whole point of relativity is to say there's no such thing as right now when you're far away.
Imagine a machine, a marvel of human ingenuity, hurtling through the void at speeds so mind-bendingly fast it could circle our entire planet in minutes. Yet, even this ultimate expression of our technological might would take millennia to reach the nearest star. This isn't a limitation of our engineering or our budget or even our willpower. It's a fundamental truth woven into the very fabric of the universe. But what if there was a loophole, a secret embedded in the laws of physics that could allow a single human life to stretch across unimaginable cosmic distances, aging mere decades while the stars outside flicker for millions of years? Prepare to have your understanding of space, time, and human potential shattered as we reveal how far one lifetime can truly travel. The fastest human-made objects, epitomized by the Voyager probes, offer a sobering perspective on our current technological limits. Voyager 1, for instance, cruises through interstellar space at approximately 38,000 miles per hour, a speed that feels immense by earthly standards. However, this velocity equates to a mere 0.006% of the speed of light. At this speed, reaching our nearest stellar neighbour, Proxima Centauri, would demand over 70,000 years of travel, far exceeding any human lifespan. Even the Parker Solar Probe, which achieves incredible speeds during its perihelion passes around the Sun, peaking at over 430,000 miles per hour, still only reaches about 0.6% of light speed. While remarkable for a spacecraft, this velocity reduces the journey time to Proxima Centauri to only 6,600 years, still an insurmountable barrier for human voyagers. The fundamental limitation stems from the propulsion methods currently available to us, primarily chemical rockets. These rockets operate on the principle of expelling mass at high velocity to generate thrust, a concept elegantly described by the Tsiolkovsky rocket equation. However, this equation reveals a harsh reality. To achieve higher velocities, an exponentially greater amount of propellant is required. For instance, reaching even 1% of the speed of light using chemical rockets would demand a fuel-to-payload ratio so astronomically high that it defies any practical engineering. The spacecraft would effectively be a fuel tank with a minuscule payload. The energy requirements for interstellar travel are equally daunting. Kinetic energy, which is the energy of motion, increases with the square of velocity. This means that doubling a spacecraft's speed quadruples its energy demand. To accelerate a substantial spacecraft, one capable of supporting human life, to even a fraction of light speed would necessitate energy outputs comparable to, or even exceeding, the total energy consumption of entire nations for years. Such power generation and containment systems lie far beyond our current capabilities. When we apply the cold, hard math to the prospect of reaching even the closest star system, the numbers become profoundly discouraging. Proxima Centauri is approximately 4.2 light-years away. A light-year, by definition, is the distance light travels in one Earth year, roughly 6 trillion miles. To cover this distance within a reasonable human lifespan, say 40 years of travel time, would require an average speed of about 10% of the speed of light. As previously established, achieving even this modest relativistic velocity with current technology is simply not feasible. The chasm between what we can currently achieve and what is necessary for interstellar human travel is not merely large, it is, for all intents and purposes, infinite with our current propulsion paradigms. This stark reality forces us to confront the limitations of our current understanding and search for entirely new physics to bridge this immense gap. To surmount the insurmountable barrier of chemical propulsion, we must look toward the violent heart of matter itself. The first logical step away from the chemical rocket is the nuclear option. This is not science fiction, it is forgotten history. In the late 1950s and early 1960s, physicists and engineers worked on Project Orion, a design that proposed propelling a spacecraft by detonating a series of atomic bombs behind it. A massive pusher plate, mounted on shock absorbers, would catch the plasma wave from the explosions, shoving the vessel forward with immense force. The physics of Orion were sound. Unlike chemical rockets which sip fuel to create a continuous but weak thrust, Orion offered high specific impulse and high thrust simultaneously, the holy grail of rocketry. Theoretical calculations suggested an Orion vessel could reach perhaps 3% to 5% of the speed of light. While still agonizingly slow for a human lifespan, Proxima Centauri would be over a century away, it represented a quantum leap over the Voyager probes. However, the Partial Testban Treaty of 1963, combined with the terrifying prospect of launching hundreds of nuclear devices into orbit, grounded the project. Yet the concept remains the brute force baseline. If we truly want to leave the solar system, we must harness the energy density of nuclear reactions, whether through pulsed fission or the far more difficult yet cleaner prospect of nuclear fusion. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. Fusion propulsion, the engine of the stars, offers a theoretical exhaust velocity far higher than fission. The British Interplanetary Society's Project Daedalus in the 1970s envisioned a two-stage fusion craft. By compressing pellets of deuterium and helium-3 with lasers to induce fusion, such a ship could theoretically reach 12% of the speed of light. Now, the math begins to look plausible. A 40-year trip to another star is technically survivable. But the engineering challenges are titanic. The ship would need to be massive, mining the atmosphere of Jupiter to gather the necessary helium-3 fuel, and the containment of a continuous fusion reaction, a miniature sun, remains a technology we have yet to master even for terrestrial power plants, let alone for a starship hurtling through the void. However, both fission and fusion are still shackled by the Tsiolkovsky equation. They still require the ship to carry its own fuel. As the ship accelerates, it must push the mass of the remaining fuel, creating a diminishing return on energy investment. To truly break the speed limit, we must abandon the idea of the self-contained ship. We must separate the engine from the vehicle. This line of thinking leads to the concept of beamed propulsion, most famously realized in the Breakthrough Starshot initiative. The logic is elegant. Keep the heavy power source on Earth or in orbit, and send only the payload. By constructing a gigawatt-class laser array or a microwave emitter, we could fire a concentrated beam at a light sail, a mirror incredibly thin and light. The pressure of the photons striking the sail would accelerate it. Because the spacecraft carries no fuel, its mass is negligible, allowing for acceleration forces that would crush a human. Starshot proposes sending gram-scale Starship probes at 20% of the speed of light. At this velocity, the journey to Alpha Centauri takes only 20 years. We could see close-up images of another solar system within a single generation. But the speed problem creates a new paradox here: stopping. A ship riding a laser beam from Earth has no way to slow down once it reaches its destination. It would zip through the Proxima Centauri system in minutes, a fleeting tourist snapping blurry photos before vanishing into the eternal darkness beyond. To stop, one would need a decelerating laser at the destination, which implies we must have already gone there to build it. Thus, beamed propulsion, while promising for reconnaissance, remains a one-way ticket for unmanned probes, not a solution for human migration. If we insist on human travel, and if we acknowledge that 10% or even 20% of light speed is the absolute maximum for matter-based propulsion, we run into the weight calculation. This is a maddening variable in interstellar economics. Suppose we launch a generation ship today, travelling at 1% of the speed of light. It will take 400 years to reach Proxima Centauri. 2 centuries later, technological breakthroughs allow us to build a ship capable of 10% light speed. The second ship, launched 200 years after the first, will overtake the older vessel in deep space and arrive at the destination centuries before the first colonizers. The crew of the first ship would arrive only to be greeted by the great-great-grandchildren of the second crew, who have already established a civilization. This suggests that for any given speed less than relativistic velocity, the optimal move is almost always to wait for better technology. The speed problem thus induces a paralysis of action. The best time to leave is always later. To escape this paralysis, theoretical physics gazes toward the forbidden territory of superluminal, faster-than-light travel. This realm is guarded by Einstein's special relativity, which dictates that as an object with mass approaches the speed of light, its mass becomes infinite and the energy required to accelerate it further becomes infinite. To bypass this, we must stop moving through space and start moving space itself. This is the principle behind the Alcubierre drive. Proposed by physicist Miguel Alcubierre in 1994, this theoretical engine does not accelerate the ship. Instead, it contracts space-time in front of the vessel and expands it behind. The ship rests in a warp bubble of flat space, surfing a wave of distorted geometry. Inside the bubble, the ship feels no acceleration. It is stationary relative to its local space. But relative to the outside observer, the bubble can move faster than light. Mathematically, this solution works. Physically, it is a nightmare. To warp space-time in this manner requires negative energy, or exotic matter, substances that possess negative mass. We have never observed such matter in the macroscopic universe. Furthermore, recent calculations suggest that the energy required to create a warp bubble just a few meters across would equal the mass energy of the planet Jupiter. While subsequent refinements have lowered these energy requirements, the Alcubierre drive remains a mathematical curiosity rather than an engineering blueprint. It also introduces the causality paradox. If you can travel faster than light, you can, under certain geometries, travel back in time. A universe that allows warp drives is a universe that allows time travel, which opens the door to logical contradictions that reality seems to aggressively prevent. Assuming we remain bound by Einstein's laws, and assuming we can achieve a significant fraction of light speed, say 90%, we encounter the phenomenon of time dilation. This is the soft solution to the speed problem. For the travellers on a ship moving at 99.9% of the speed of light, the journey to the centre of the galaxy, 30,000 light-years away, might feel like only a few decades. They could explore the universe within a human lifetime, but this comes at a terrible cost. While 20 years pass for the crew, 30,000 years pass on Earth. This time wall means that high-speed interstellar travel is essentially a form of exile. To leave Earth at relativistic speeds is to witness the death of everyone you ever knew, the fall of your civilization, and the geological reshaping of your home planet, all in the span of a shipboard breakfast. The speed problem therefore transforms from a technological hurdle into a sociological existential crisis. The faster you go, the more isolated you become. A civilization of relativistic travellers would be a diaspora of ghosts, untethered from time, visiting worlds that have long since forgotten who sent them. Given these immense physical and temporal barriers, the solution to the speed problem might not be to move faster, but to live longer. If we cannot shrink the distance, we must expand the traveller. This leads to the concept of the generation ship or the sleeper ship. A generation ship does not attempt to beat the speed of light. It accepts the slowness. It is a world ship, a self-contained biosphere travelling at a humble 0.5% of light speed. The journey will take thousands of years. The social engineering required for such a vessel is far more complex than the rocket science. How do you maintain a stable society in a metal can for 50 generations? How do you prevent mutiny, despair, or the loss of technical knowledge? The middle generations, those born on the ship who will die on the ship, never seeing the Earth that was left behind nor the planet that is the destination, would arguably be prisoners of their ancestors' ambition. The moral implications of condemning unborn generations to a life in the void are profound. The alternative is the sleeper ship, cryonics. If we can master the art of suspended animation, the duration of the trip becomes irrelevant to the traveller. The speed problem vanishes if the subjective time for the pilot is 0. However, this demands a biology that we do not possess. We are not tardigrades. Our cells crystallise and shatter when frozen. Perfecting stasis requires rewriting human biology, or mastering nanotechnology to repair cellular damage in real time. Perhaps ultimately the speed problem is only a problem for biological entities. The fragility of the human body, its need for gravity, radiation shielding air and water, and its pathetic lifespan, makes us poor candidates for the stars. The solution may be the post-biological approach. We may never go to the stars in meat sacks. We may send our minds. If we can upload human consciousness into a digital substrate, or if we develop strong artificial general intelligence, AGI, the constraints change entirely. A digital consciousness can be paused. A silicon-based entity can withstand thousands of Gs of acceleration. It can survive hard vacuum and cosmic radiation with minimal shielding. Most importantly, it can be transmitted. We could send a fleet of self-replicating von Neumann probes to Proxima Centauri at 20% light speed. Upon arrival, they mine the local asteroids, build a receiver station, and then we beam ourselves there at the speed of light as data. In this scenario, the top speed of travel is exactly the speed of light, c. The travel time is just the latency of the data stream. We would not inhabit the exoplanets physically. We would inhabit the virtual worlds running on the servers built by our robotic precursors, orbiting a red dwarf star. The physical universe becomes merely the hardware rack for the software of our civilization. The speed problem, viewed through this lens, is a filter. It suggests that the Star Trek vision of the future, humans in starships warping between worlds, is an archaic fantasy rooted in the age of sail. The universe is too vast and the speed of light too slow for biological empires. The true interstellar civilizations, if they exist, are likely not travelling in ships at all. They are propagating as information, expanding at the speed of light, silent and invisible, waiting for us to build a receiver capable of hearing them. Until then, we remain trapped in our gravity well, staring at the speedometer, wishing the numbers would go higher, while the laws of physics stubbornly whisper, no. The universe, in Einstein's revolutionary view, is not a fixed stage upon which events unfold, but a dynamic, interwoven fabric called spacetime. This fabric is not merely a backdrop. It actively participates in the cosmic drama, bending and curving under the influence of mass and energy, and dictating the paths of everything within it. Our intuitive understanding of space as three separate dimensions and time as a constant independent flow is profoundly mistaken. Instead, space and time are inextricably linked, forming a four-dimensional continuum where motion through one affects the other. Central to Einstein's Special Relativity, published in 1905, is the astonishing realization that the speed of light in a vacuum is constant for all observers, regardless of their own motion. This seemingly simple postulate has profound consequences, acting as a universal speed limit that no object with mass can ever reach. This limit is not merely an engineering challenge, it is a fundamental law of physics. As an object accelerates, its mass effectively increases, requiring ever greater amounts of energy to achieve further acceleration. Reaching the speed of light would require infinite energy, an impossibility. However, within this universal speed limit lies a remarkable loophole: time dilation. This phenomenon, a direct consequence of the constant speed of light, dictates that time passes more slowly for an object in motion relative to a stationary observer. The faster an object moves, the more pronounced this effect becomes. This means that for a traveller moving at a significant fraction of the speed of light, their clocks would tick more slowly than clocks left behind on Earth. They would age less during a journey than their counterparts who remained stationary. This is the first tantalizing hint that our traditional understanding of time as an absolute and unyielding constant is flawed, and that it might offer a pathway to traverse vast cosmic distances within a human lifespan. The connection between space and time is further illuminated by this concept. As an object's velocity increases, its motion through space is, in a sense, traded for motion through time. More specifically, its rate of passage through time slows down. This is not a trick of perception or a malfunction of clocks. It is a fundamental property of space-time itself, where the measurement of distance and the passage of time are relative to the observer's frame of reference. This interconnectedness means that any attempt to understand how far humans can travel must necessarily account for the dynamic and flexible nature of time. To fully grasp the magnitude of this temporal elasticity, we must move from abstract equations to the visceral reality of what is known as the twin paradox. This famous thought experiment, often cited but rarely fully appreciated, serves as the ultimate illustration of special relativity's impact on human existence. Imagine two identical twins, Alice and Bob. Alice remains on Earth, while Bob boards a spacecraft capable of constant acceleration, propelling him to a velocity of 99% the speed of light. He travels to a distant star system, 10 light-years away, and then returns. From Alice's perspective, the journey is straightforward. She watches Bob's ship recede, knowing that at near-light speed, the round trip will take roughly 20 years. She ages 20 years, waiting for his return. However, inside the ship, Bob's reality is radically different. Because he is moving through space at such a high velocity, his movement through time has slowed dramatically relative to Earth. To Bob, the distance to the star seems to have contracted, a phenomenon known as length contraction, the spatial counterpart to time dilation. For him, the journey does not take 20 years, it might take only 3. When he steps out of the airlock back on Earth, He's biologically 17 years younger than his twin sister. His cells have divided fewer times. His heart has beaten fewer times. His memories span a shorter duration. This is not an illusion or a biological preservation technique. Bob has literally travelled into Earth's future by taking a shortcut through time. This realization shatters the Newtonian concept of simultaneity. In our everyday lives, we assume that now is a universal moment shared by everyone in the cosmos. If a star explodes in the Andromeda galaxy right now, we assume it happens at the same instant we check our watches, even if the light won't reach us for millions of years. Einstein proved this is false. Now is a relative concept, dependent entirely on the observer's velocity and location. For an alien civilization moving towards Earth at high speed, their now might include our future. For one moving away, their now might align with our past. The universe does not tick to a single master clock. Instead, every particle in the universe carries its own personal time, ticking at a rate determined by its unique path through the fabric of spacetime. However, special relativity was only the first half of Einstein's restructuring of reality. In 1915, he expanded his vision to include gravity, culminating in the general theory of relativity. If special relativity describes how space and time behave for observers moving at constant speeds, general relativity explains what happens when mass enters the equation. Einstein realized that the force of gravity, which Isaac Newton described as an invisible tether pulling objects together, was actually an illusion. What we perceive as gravity is simply the curvature of space-time itself. Imagine a tightly stretched trampoline. If you place a heavy bowling ball in the center, the fabric dips, creating a curved depression. If you then roll a marble across the trampoline, it will not travel in a straight line. It will curve around the bowling ball. To the marble, it feels as though it is being pulled toward the center, but in reality, it is simply following the straightest possible path, a geodesic, along a curved surface. In the cosmic arena, the bowling ball is a star or a planet and the marble is a spaceship, a moon, or even a ray of light. Mass tells spacetime how to curve, and spacetime tells mass how to move. This geometric interpretation of gravity has profound implications for time. Just as velocity slows down time, so does gravity. This is known as gravitational time dilation. The closer you are to a massive object, the deeper you are in the gravity well, and the slower time flows relative to an observer further away. This is not merely theoretical. It is a daily operational reality for the Global Positioning System (GPS). The satellites orbiting Earth are in a weaker gravitational field than the users on the ground. Consequently, their onboard atomic clocks tick faster than clocks on Earth's surface by about 45 microseconds per day. Simultaneously, their orbital velocity makes them tick slower by about 7 microseconds per day. The net result is that time runs faster for the satellites. If engineers did not program the system to account for Einstein's relativistic effects, GPS accuracy would drift by kilometers every single day, rendering the entire system useless. The most extreme manifestation of gravitational time dilation occurs at the boundary of a black hole, the event horizon. Here, the curvature of space-time becomes infinite. If a brave astronaut were to fall toward a black hole while you watched from a safe distance, you would never see them cross the horizon. As they approached the point of no return, the light coming from them would become increasingly red-shifted as it struggled to climb out of the gravity well. More disturbingly, their time would appear to slow down until it froze completely. To the outside observer, the astronaut would appear to be plastered against the horizon, timeless and immobile, fading slowly from view. Yet, for the astronaut, the experience would be terrifyingly quick. They would cross the horizon in a finite amount of their own time, unaware that they had just severed their causal link with the rest of the universe. Inside the horizon, the roles of space and time switch. The singularity at the center is no longer a location in space. It becomes a moment in the future, an inevitable Tuesday that you cannot avoid, no matter which direction you turn. This malleability of space-time raises a tantalizing question. If space can bend, can it be folded? Can we cheat the universal speed limit not by moving through space, but by manipulating space itself? This is the realm of theoretical solutions to Einstein's field equations, such as the Einstein-Rosen bridge, more commonly known as a wormhole. A wormhole acts as a tunnel connecting two distant points in space-time. Imagine drawing two dots on a piece of paper, representing Earth and Alpha Centauri. The shortest distance between them is a straight line, but if you fold the paper so the two dots touch, the distance becomes 0. A wormhole does exactly this to the four-dimensional fabric of the universe. If such a structure could be created and stabilized, a feat requiring exotic matter with negative energy density to keep the throat of the wormhole open against the crushing force of gravity, a traveller could step through and emerge light years away instantly. Because they never technically exceeded the speed of light locally, they just took a shortcut. They would not violate the tenets of relativity. Similarly, the concept of the Alcubierre drive proposes a warp bubble that contracts space in front of a starship and expands it behind. The ship would sit in a bubble of flat, unmoving space, while the bubble itself surfs a wave of space-time distortion. Since space itself can expand or contract faster than light, as it did during the Big Bang, the ship could technically arrive at a destination faster than a light beam, without the ship itself ever moving locally. These concepts remain firmly in the realm of advanced theoretical physics, requiring energy scales and materials we cannot yet manipulate, but they are mathematically consistent with Einstein's universe. They serve as a reminder that the speed of light is a barrier for objects moving through the fabric, but perhaps not for the fabric itself. Ultimately, Einstein's revolution leads us to a philosophical precipice known as the block universe. If time is a dimension similar to length, width, and height, and if the distinction between past, present, and future is merely an illusion of human consciousness, then the universe can be viewed as a static, four-dimensional block. In this view, the dinosaur extinction, the building of the pyramids, your birth, and your death all exist simultaneously within the space-time manifold. We simply experience the slice of the block that our consciousness is currently illuminating, much like a spotlight moving across a dark stage. The actors and sets in the darkness are still there, they are just not currently lit. This perspective challenges our notions of free will and destiny. If the future already exists in the geometry of space-time, waiting for us to arrive at its coordinates, then the flow of time is not a creation of new events, but a discovery of pre-existing ones. It suggests a universe of breathtaking determinism and grandeur, where every event is a fixed point in a magnificent eternal structure. Thus, Einstein's legacy is not just a set of formulas for calculating planetary orbits or the energy of an atom. It is a fundamental reordering of our relationship with reality. We are not inhabitants of a 3D box ticking along to a universal metronome. We are travellers on world lines, threading our way through a flexible, curving, four-dimensional landscape where gravity is geometry, time is relative, and the only constant is the speed of light. We live in a universe where the faster we go, the longer we live, where heavy objects stop time, and where the separation between here and there or now and then is not absolute, but a matter of perspective. In this dynamic cosmos, we are woven into the very fabric we seek to understand, subject to the warping and weaving of a reality far more strange and beautiful than our intuition could ever conceive. The concept of time as a universal and unwavering constant is deeply ingrained in our everyday experience, yet it is fundamentally challenged by the principles of special relativity. One of the most counterintuitive aspects of this theory is the relativity of simultaneity, which states that two events observed as happening at the same time by one observer may not be simultaneous for another observer moving relative to the first. There is no absolute now that all observers can agree upon across the vastness of space. This profoundly alters our understanding of causality and the very fabric of reality. Experimental proof of time dilation, while subtle at everyday speeds, is abundant and undeniable. Perhaps the most famous and direct confirmation comes from the Hale-Keating experiment in 1971. Scientists flew atomic clocks around the world on commercial airliners, both eastward and westward, and then compared their readings to identical clocks that remained stationary at the US Naval Observatory. The flying clocks, though moving at relatively minuscule speeds compared to light, showed minute but measurable differences in time compared to their stationary counterparts, precisely as predicted by both special and general relativity. The clocks that travelled eastward, against Earth's rotation, lost a small amount of time, while those travelling westward, with Earth's rotation, gained time. Relativistic effects are not just theoretical curiosities, they have practical applications that impact our daily lives. The Global Positioning System, or GPS, relies heavily on the precise accounting of relativistic effects. GPS satellites orbit Earth at high speeds and experience weaker gravitational fields than receivers on the ground. According to special relativity, the clocks on the satellites run slower due to their velocity. According to general relativity, they run faster due to the weaker gravity. These two effects partially cancel each other out, but a net relativistic effect remains. If these relativistic corrections were not applied, GPS systems would accumulate errors of many kilometers per day, rendering them useless for accurate navigation. This real-world application underscores that time is indeed a variable, not a constant, its passage influenced by motion and gravity. The twin paradox serves as a classic thought experiment to illustrate the profound implications of time dilation. Imagine identical twins. One twin embarks on a high-speed journey to a distant star and back, travelling at a significant fraction of the speed of light. The other twin remains on Earth. When the travelling twin returns, they will find that they have aged less than their stay-at-home sibling. This is not a matter of subjective perception or biological wear and tear. It is a measurable, physical difference in their ages. The paradox arises from the apparent symmetry of their motion. Each twin sees the other as moving. But the resolution lies in the fact that the travelling twin experiences acceleration and deceleration, changing their inertial frame of reference, while the earthbound twin largely remains in a single inertial frame. This thought experiment powerfully demonstrates how time itself becomes a flexible quantity, bending and stretching based on an observer's velocity through spacetime. The resolution of the twin paradox brings us to a startling realization. The universe is not a three-dimensional stage where things happen over time, but rather a four-dimensional block of spacetime where the past, present and future arguably exist simultaneously. This concept, known as the block universe or eternalism, is the direct philosophical and physical consequence of Einstein's relativity. If there is no universal now, if my now can be your future, depending on our relative velocities, then the future must, in some sense, already represent a physical reality. Consider the Andromeda paradox, a thought experiment devised by Roger Penrose to illustrate this. Imagine two people walking past each other on the street. One is walking towards the Andromeda galaxy, which is 2.5 million light-years away, and the other is walking away from it. Despite the trivial difference in their walking speeds relative to the speed of light, the vast distance to Andromeda amplifies the slant of their respective planes of simultaneity. For the person walking towards Andromeda, their now slice of the universe might include an Andromedan space fleet launching an invasion. For the person walking away, their now slice might precede the decision to launch the fleet by days or weeks. If two people on Earth can inhabit nows that differ by days in the Andromeda galaxy simply by walking in opposite directions, it implies that the events in Andromeda are already fixed within the space-time block. The invasion is not going to happen. It exists at a specific coordinate in the four-dimensional manifold, just as a mountain exists at a specific latitude and longitude. We simply haven't encountered that coordinate yet. This view strips time of its flow. In the block universe, time does not pass. We merely move through it, much like a needle moving across a vinyl record. The entire song is etched onto the disc at once, but the listener experiences it sequentially. This challenges our deepest intuition, the sense of becoming. We feel that the past is a memory, the future is a void to be written, and the present is the only reality. Relativity suggests this is a cognitive illusion, a trick of consciousness rather than a feature of the physical universe. However, if time is a landscape we traverse, what dictates the direction? Why do we remember the past but not the future? This brings us to the arrow of time, a problem that relativity does not solve. The fundamental laws of physics, from Newton's mechanics to Einstein's relativity to Schrödinger's quantum equation, are time-symmetric. If you were to film a planetary orbit or a particle collision and play it backward, the physics would still hold true. The equations do not prefer one direction over the other, yet we never see a shattered teacup reassemble itself or an omelette turn back into an egg. The solution to the arrow of time likely lies in thermodynamics, specifically the second law, which governs entropy. Entropy is a measure of disorder, or more accurately, the number of ways a system can be arranged. There are infinitely more ways for a cup to be broken than for it to be whole. Therefore, systems naturally evolve from states of low entropy, order, to high entropy, disorder. The Big Bang was a state of exquisitely low entropy. Ever since, the universe has been sliding down the entropy gradient. Our perception of time flowing forward is essentially our consciousness registering the increase of global disorder. We are riding the wave of the universe's equilibration. In this view, time is a statistical probability, not a fundamental force. If the universe were to reach maximum entropy, a state known as heat death, all change would cease, and the arrow of time would effectively dissolve, leaving a timeless static void. While special relativity deals with velocity, general relativity introduces an even more dramatic distorter of time: gravity. We have established that gravity is not a force, but the curvature of spacetime caused by mass. This curvature stretches time just as it stretches space. This phenomenon leads to gravitational time dilation, which becomes most extreme at the boundary of a black hole known as the event horizon. To an observer watching from a safe distance, an astronaut falling into a black hole would never actually appear to cross the horizon. As the astronaut approaches the point of no return, the light bouncing off them fights against an increasingly deep gravitational well to reach the observer. This struggle causes the light to lose energy, shifting to the red end of the spectrum, gravitational redshift. Simultaneously, the information carrying the image of the astronaut arrives at slower and slower intervals. The distant observer sees the astronaut's movements slow down until they appear frozen in time, forever hovering just above the horizon, gradually fading into invisibility as the light waves stretch to infinity. Yet, for the astronaut, the experience is radically different. They cross the horizon in a finite amount of proper time measured by their own wristwatch. They would notice nothing special about the horizon itself, no signpost, no barrier. They would simply drift into a region of space-time where the geometry is so twisted that all possible paths forward lead to the singularity at the centre. Inside a black hole, the roles of space and time effectively swap. The radial distance to the centre becomes a point in time, the future. Just as you cannot stop next Tuesday from arriving, the astronaut cannot avoid the singularity. It is no longer a location they can steer away from. It is an inevitable moment in their future timeline. This malleability of space-time raises the tantalizing possibility of closed time-like curves, CTCs, the physicist's term for time travel. Einstein's field equations do not strictly forbid world lines that loop back upon themselves. If one could twist space-time violently enough, perhaps using a rotating black hole, a Kerr black hole, or a wormhole held open by exotic matter with negative energy density, it might be possible to return to a point in one's own past. However, the universe seems to possess mechanisms to protect the timeline, often referred to as chronology protection. The most famous paradox associated with CTCs is the grandfather paradox. If you travel back and prevent your grandfather from meeting your grandmother, you are never born, and thus cannot travel back to prevent the meeting. Some physicists, like Igor Novikov, propose the self-consistency principle, which argues that the probability of an event creating a paradox is zero. In this view, if you travelled back in time, you would find that you were always part of the past. Your attempts to kill your grandfather would fail, the gun would jam, or you would mistake the person, and your very presence might be the catalyst that ensures his survival. You cannot change the past, you can only fulfill it. The timeline is a single, immutable thread that may loop but never break. Another interpretation, arising from quantum mechanics, is the many worlds interpretation. This suggests that every quantum event branches the universe into alternate histories. If you travel back in time, you do not arrive in your own past, but in the past of a parallel quantum branch. You could kill the grandfather in that timeline, preventing a version of you from being born there, but your original timeline remains intact. This solves the paradox by removing the closed loop entirely, replacing it with a divergent path. This brings us to the greatest conflict in modern physics, the clash between relativity and quantum mechanics regarding the nature of time. In Einstein's relativity, time is dynamic, flexible, and woven into the fabric of the universe. It is a coordinate that warps. In quantum mechanics, however, time is treated as a rigid, absolute background parameter, a stage upon which quantum events play out, much like the Newtonian time Einstein sought to replace. The T in the Schrödinger equation is a universal clock, ticking away uniformly. This incompatibility is the primary reason we do not yet have a theory of everything. When physicists attempt to combine these two frameworks into quantum gravity, the concept of time often breaks down entirely. The The Wheeler-DeWitt equation, a potential equation for the quantum state of the universe, does not contain a time variable. It describes a universe that is static and unchanging at the most fundamental level. This suggests that time might be an emergent property, a macroscopic approximation that arises from the entanglement of quantum states, much like heat arises from the motion of atoms. At the bedrock of reality, time as we know it may not exist at all. We are left with a picture of time that is profoundly alien to our daily experience. It is not a river flowing from the past to the future. It is a dimension, inextricably linked to space, curved by matter and warped by speed. It allows for the simultaneous existence of all history and all futurity. It slows to a halt at the edge of darkness and may dissolve into nothingness at the quantum scale. Our perception of a fleeting now is a biological limitation, a necessary simplification allowing our brains to navigate a complex causal web. We are like readers engrossed in a novel, feeling the tension of the plot unfold page by page, unaware that the entire story is already written, bound, and sitting on the shelf of space-time. The study of time is, therefore, an unlearning of our intuition. The GPS satellite overhead, correcting its clock by microseconds to account for the warping of the sky, is a silent testament to the fact that we live in a universe far stranger than our senses report. We are time travelers by nature, moving through the fourth dimension at a steady pace, but the physics of the cosmos reminds us that this pace is not guaranteed. The direction is a statistical accident, and the separation between what was and what will be is, in the words of Einstein, only a stubbornly persistent illusion. At the heart of time, dilation and length contraction, lies a set of equations known as the Lorentz transformations, developed by Hendrik Lorentz before Einstein's full theory of relativity. These mathematical tools precisely describe how measurements of space and time change between different inertial frames of reference, particularly when those frames are moving relative to each other at speeds approaching that of light. The core component of these transformations is the Lorentz factor, denoted by the Greek letter gamma, dr. Gamma is calculated as 1 divided by the square root of 1 minus v squared over c squared, where v is the object's velocity and c is the speed of light. As velocity v approaches the speed of light c, the term v squared over c squared approaches 1, making the denominator approach 0, and thus gamma approaches infinity. This gamma factor dictates how much time passage is affected by velocity. Specifically, the time experienced by a moving object, proper time, is equal to the time measured by a stationary observer divided by gamma. This means that as gamma increases, the proper time experienced by the traveller decreases relative to the stationary observer. The exponential nature of relativistic effects becomes strikingly clear when examining the gamma factor's behaviour. At low velocities, gamma is very close to 1, meaning time dilation is negligible. For example, at 1% of light speed, gamma is only about 1005, meaning a traveller would age just 5% less than someone on Earth. However, as velocity climbs higher, gamma begins to increase dramatically. At 50% of light speed, gamma is approximately 1.15. At 90% of light speed, gamma jumps to 2.29. Reaching 99% of light speed pushes gamma to about 7.08. This means that for every 7.08 years that pass on Earth, a traveller at 99% of light speed would experience only 1 year. This mathematical reality highlights why simply getting close to light speed isn't enough for truly transformative interstellar travel. Even 99.9% of light speed, while seemingly extremely fast, yields a gamma factor of approximately 22/36. While this provides significant time dilation, allowing a round trip to a star 100 light-years away to be completed in about 9 years of ship time, Earth would still age roughly 447 years. For a human lifespan to encompass truly vast distances, gamma needs to be far, far higher. To travel across thousands or even millions of light-years within a subjective human lifetime, velocities must be so incredibly close to light speed that the gamma factor reaches thousands, millions, or even billions. This means adding many more nines after the decimal point in the velocity's percentage of light speed, pushing the mathematics to its extreme limits. The mathematics of approaching light speed is not linear. It is a steep, exponential climb. where each additional fraction of a percentage point of light speed demands an enormous leap in the gamma factor, and, consequently, in the energy required. To fully grasp the mathematics of forever, we must venture beyond the comfortable low-digit gamma values of 2 or 7 and explore the vertiginous heights of the asymptote. This is the realm where the decimal expansion of light speed, 0.999, determines the fate of civilizations. The difference between 99.9% and 999% of the speed of light is not merely a matter of fractional velocity. It is the difference between visiting a neighbour and traversing the observable universe. Let us consider the specific numbers required to unlock the galaxy. The Milky Way is roughly 100,000 light-years in diameter. To a stationary observer on Earth, any journey across this expanse must take at least 100,000 years. However, the pilot of a starship is concerned with their own biological clock, or proper time. To cross the entire galaxy within a single human lifetime, let us designate a comfortable 20-year ship time journey. The gamma factor must be approximately 5,000. Plugging back into the Lorentz equation requires a velocity. That is 7 nines past the decimal point. At this speed, the galaxy, which appears to us as a vast, spiralling disk of incomprehensible scale, would undergo a relativistic length contraction. To the pilot, the 100,000 light-year distance would shrink to a mere 20 light-years. The pilot does not feel they are moving faster than light. Rather, they perceive that the universe has flattened in the direction of travel, bringing the destination closer to them. But let us think bigger. To reach the Andromeda Galaxy, our nearest major neighbour located 2.5 million light-years away, in that same 20-year biological window, we need a gamma factor of 125,000. This demands a velocity, 10 nines. At this speed, the space between galaxies, an abyss that boggles the human mind, contracts to the scale of a suburban commute. If we push even further to a gamma of 1 billion, the entire observable universe, spanning some 93 billion light-years, could be traversed in a subjective lifetime. This is the seduction of the asymptotic curve. The universe is theoretically accessible to a mortal lifespan, provided one can hug the speed of light tightly enough. However, the universe exacts a toll for this access, paid in the currency of energy, the relativistic kinetic energy equation. This formula reveals a terrifying energy cliff. As gamma climbs linearly, energy requirements do not just grow, they explode. At a gamma of 1, rest, energy is 0. At a gamma of 2, the energy required to accelerate the ship is equal to the mass energy of the ship itself. You would need to convert an amount of fuel equal to the weight of your starship into pure energy with 100% efficiency to reach this speed. But for our galactic, the energy requirement is 5,000 times the mass energy of the vessel. To accelerate a modest 100-ton spacecraft to this velocity would require an energy output roughly equivalent to the total energy consumption of the human race for several millennia, all focused into a single engine burn. And this assumes perfect conversion of mass to energy, a feat physically impossible for chemical or even fission rockets. Only antimatter-matter annihilation comes close to this efficiency, and even then, the fuel tanks would need to be thousands of times larger than the ship itself. The rocket equation becomes a tyranny of exponential mass. To go faster, you need more fuel, which adds mass, which requires more fuel to accelerate. Furthermore, as the spacecraft climbs the ladder of nines, the environment outside changes from a vacuum into a particle accelerator aimed directly at the cockpit. This is the problem of the interstellar medium ISM. Space is not truly empty. It is filled with stray hydrogen atoms, dust grains, and cosmic rays. At low speeds, these are harmless. A single hydrogen atom impacts the ship's hull with the energy of a high-energy particle beam. This creates a phenomenon known as relativistic blue shift. Just as the siren of an approaching ambulance is pitched higher, the electromagnetic waves coming from ahead of the ship are compressed. The gentle cosmic microwave background, CMB, the cold afterglow of the Big Bang that permeates the universe, is Doppler shifted into the visible spectrum, then into ultraviolet, and finally at high enough gamma into X-rays and gamma rays. A ship travelling at high relativistic speeds would be flying into a blinding wall of fire. The visible light from stars ahead would shift into hard radiation, capable of frying electronics and DNA instantly. The shielding required to survive this bombardment, kilometers of lead or water or massive magnetic fields, adds more mass, which in turn demands more energy, creating a vicious cycle that makes high gamma travel an engineering nightmare. The visual experience of the traveller would be equally alien to our intuition. Science fiction often depicts star streaks passing by the windows. The reality of the mathematics of forever is far stranger, due to an effect called relativistic aberration, or beaming. As velocity increases, the angles of light rays from objects around the ship are tilted toward the direction of motion. The field of view condenses. Stars that are actually to the side or even slightly behind the ship would appear to move into the forward field of view. At extreme gamma, the entire visible universe behind the ship would go dark as the light struggles to catch up. Meanwhile, the view ahead would shrink into a concentrated, intensely bright disk of light, a searchlight encompassing all the stars the ship is approaching, blue shifted into a piercing violet or invisible radiation point. The traveller would effectively be flying down a dark tunnel toward a singularity of light, with the rest of the cosmos squeezed into that single, blinding eye. There is also a profound topological consequence to this math, the isolation of the event horizon. We typically associate event horizons with black holes, points of no return, but special relativity dictates that an accelerating observer creates a Rindler horizon behind them. If a spaceship accelerates with constant 1g force to provide artificial gravity, there is a point in space behind the ship from which light can never catch up to the vessel as long as it keeps accelerating. The ship effectively disconnects itself from a portion of the universe's past. Signals sent from Earth might chase the ship forever, never closing the gap. The crew would not just be far away, they would be causally severed from their home for the duration of the burn. This brings us to the most crushing realization of the gamma factor, the time divorce. The mathematics of high gamma travel makes the universe accessible in space, but inaccessible in time. The symmetry of the Lorentz transformation is brutal. If you travel to the Andromeda galaxy, the 2.5 million light-year journey takes you 20 years, but while you read books, eat meals, and age 20 years, 2.5 million years pass on Earth. This is not merely missing a birthday or a generation, this is geological time. When you arrive at Andromeda, the light from Earth that reaches you will show the planet as it was when humans were just learning to sharpen stones, if you look back 2.5 million years. But if you turn around and come back at the same speed, another 2.5 million years will pass. The round trip takes 40 years of your life, but you return to an Earth 5 million years in the future. The humanity you knew is gone. The languages, the cultures, the cities, eroded to dust. The continents themselves will have shifted positions due to plate tectonics. The ecological biosphere may be unrecognizable. You would return not as a hero, but as a ghost, an archaeological anomaly from a forgotten epoch. The mathematics of forever implies that interstellar travel at relativistic speeds is effectively a one-way trip, even if you return to the same coordinate. You're trading your place in time for movement in space. You can traverse the width of the universe, but only if you're willing to abandon your era. This temporal displacement creates a chronological horizon. A civilization that sends out high-speed colonization fleets is planting seeds it will never see sprout. The colonies will be established in the deep future of the home planet. Communication becomes impossible not just because of the speed of light delay, but because the societies are existing at different rates of temporal flow. A message sent from Earth to a ship moving at high gamma might be received by the ship a few days later, ship time, but the reply, sent immediately, would reach Earth thousands of years later. There can be no dialogue, only monologues thrown into the void. Finally, we must consider the limit, the photon itself. A photon travels into the Lorentz factor, the denominator becomes zero, and gamma becomes infinite. For a photon, proper time is zero. From the perspective of a particle of light, the moment it is emitted by a star in a distant galaxy, and the moment it strikes your retina on Earth are simultaneous. There is no passage of time. The distance between the star and your eye is length contracted to zero. This suggests that from the standpoint of light, the fundamental carrier of information in the universe, space-time collapses into a single point of interaction. The photon exists in an eternal now, bridging vast distances instantly in its own frame. Our struggle with the mathematics of forever is essentially a struggle against our own mass. We are heavy, sluggish creatures anchored to the slow ticking of the cosmic clock by the Higgs field, which grants us mass. To transcend the vastness of the cosmos, we must shed the weight of matter or master the geometry of space-time itself. Until then, the gamma factor stands as the ultimate gatekeeper. It taunts us with the possibility of the infinite, giving us the mathematical permission to cross the universe, while enforcing a physical toll that ensures we can never truly share the journey with those we leave behind. We can have the universe, or we can have each other, but the math suggests we cannot easily have both. The forever in the mathematics is not just about the infinite reach of the traveller, but the eternal silence that grows between them and their home. Just as time is not an absolute constant, neither is space. Special relativity reveals that space itself contracts in the direction of motion for an object moving at relativistic velocities. This phenomenon, known as length contraction, means that an object appears shorter to a stationary observer along the direction of its motion, proportional to the Lorentz factor. From the perspective of the traveller, however, it is the distances between stars and galaxies that appear shortened, making their journey seem shorter as well. The geometry of shortened distances is a direct consequence of the constant speed of light. If a light signal must cover a distance at a constant speed, and time itself is dilating for the moving observer, then the perceived distance must also change to maintain the constancy of light speed in all inertial frames. From the perspective of a traveller moving at a significant fraction of light speed, the universe ahead of them compresses. The 4.2 light-years to Proxima Centauri, for example, would appear significantly shorter to a relativistic spacecraft, effectively bringing the destination closer. The visual effects at relativistic speeds would be nothing short of bizarre. Beyond the blue shifting of light from ahead and red shifting from behind, length contraction would cause objects in the direction of motion to flatten and appear distorted. Stars themselves would appear to shift their positions, seemingly moving closer together and bunching up in the direction of travel, while the space perpendicular to the direction of motion would remain unaffected. This means that the familiar constellations would become unrecognizable, compressed into a narrow cone of light directly ahead of the spacecraft. The role of reference frames is crucial here. An observer on Earth measures the proper length of a distant star system, but a traveller moving at relativistic speeds exists in a different reference frame, and from their perspective it is the distance between the star systems that is contracted. Both measurements are equally valid within their respective frames. There is no true length. Length is relative to the observer's motion. Ultimately, the universe looks profoundly different at high speeds. The cosmic landscape transforms from a static, vast expanse into a dynamic, shifting panorama where distances shrink, colours distort, and time itself bends. This relativistic universe, though alien to our everyday experience, is the true stage for any attempt at interstellar travel, making the seemingly impossible journey within a human lifetime, from the traveller's perspective, a far more manageable proposition. To understand the full magnitude of length contraction, we must venture beyond the simple linear shortening of distances and explore the profound structural and paradox-inducing consequences of this phenomenon. It is not merely that the destination gets closer, it is that the physical definition of solid and simultaneous begins to fracture under the pressure of relativistic speed. The universe does not just shrink, it reorganizes itself to preserve the sanctity of the speed of light, leading to scenarios that defy human intuition and challenge the very concept of objective reality. One of the most mind-bending implications of length contraction is captured in the classic thought experiment known as the ladder paradox, or the barn pole paradox. Imagine a ladder that is exactly 10 meters long and a barn that's only 8 meters deep, with a front door and a back door. In a static, non-relativistic world, the ladder clearly cannot fit inside the barn. If you try to store it, 2 meters will stick out. However, if a runner carries the ladder at a significant percentage of the speed of light, let's say 80%, the ladder undergoes length contraction from the perspective of a stationary observer sitting on the roof of the barn. To this observer, the 10-meter ladder contracts to 6 meters. Mathematically and physically, the ladder is now shorter than the barn. For a fleeting moment, as the runner sprints through, the observer can close both the front and back doors simultaneously, trapping the entire ladder inside the barn before opening them again to let the runner exit. However, from the runner's perspective, the situation is reversed. Relativistic physics dictates that the runner is stationary in their own frame of reference, and it is the barn that is moving toward them at 80% the speed of light. Consequently, the runner sees the barn undergo length contraction. The 8-meter barn shrinks to 4.8 meters. The runner is now carrying a 10-meter ladder toward a microscopic 4.8-meter shed. There is seemingly no physical way for the ladder to fit inside. How then can the observer on the roof claim the doors were closed while the ladder was inside? The resolution to this paradox lies in the breakdown of simultaneity, a direct cousin of length contraction. In the runner's frame of reference, the doors do not close at the same time. The leading event, the back door closing, and the trailing event, the front door closing, happen at different moments. The runner sees the front of the ladder exit the back of the barn before the back door closes, and long after that, the front door closes behind the trailing edge of the ladder. Both observers are correct. The ladder fits in the barn in one frame and does not in the other. Length contraction proves that fitting inside is not an absolute spatial property of objects, but a relative temporal relationship between the object and its container. Space is mutable, dependent entirely on the velocity of the observer. This mutability extends to the very density of the universe. As a spacecraft accelerates to high relativistic speeds, the volume of the space it traverses contracts. If the distance to a star shrinks by a factor of 10, the empty space containing interstellar hydrogen and dust also shrinks. While the ship itself remains normal to the pilot, the universe ahead becomes compacted. This has terrifying implications for structural integrity and shielding. The interstellar medium, usually a harmless vacuum with a few atoms per cubic centimetre, is length contracted into a dense bombardment. To the relativistic traveller, the tenuous gas between the stars is compressed into a high-density fluid. Impacting a hydrogen atom at 99.9%, the speed of light is not like hitting gas. It is like being hit by a particle beam accelerator. The flux, the number of particles hitting the ship per second, skyrockets not only because the ship is moving fast, but because the space containing those particles has physically shortened. The ship is sweeping through a light year of dust in a fraction of the time, effectively facing a wall of matter. This means that length contraction turns the vacuum of space into a hostile, abrasive medium. A journey that shortens the distance to Alpha Centauri also concentrates the radiation and debris of the entire journey into a much shorter, more intense exposure window. The short road is also the hot road. Furthermore, we must distinguish between what is measured and what is seen. Length contraction describes the physical measurement of space, but the visual experience is complicated by the finite speed of light reaching the traveller's eyes. This leads to the Penrose-Terrell rotation. If a sphere passes an observer at relativistic speeds, one might expect it to look like a flattened pancake due to length contraction. However, because light from the back of the sphere takes longer to reach the observer than light from the front, the visual distortion actually makes the sphere appear rotated rather than flattened. For a traveller moving through a field of stars, this creates a dizzying optical illusion. As the spacecraft accelerates, stars are not just blue-shifted, they appear to rotate and cluster. This effect, known as relativistic aberration, or beaming, acts like a cosmic zoom lens. The light from stars that are physically located to the side of the spacecraft, at 90 degrees to the direction of motion, is tilted forward. As the ship approaches the speed of light, the entire visible universe, including stars that should be behind the pilot's peripheral vision, begins to slide forward into the field of view. Eventually, at extreme velocities, the view to the sides and rear turns pitch black. The entire sky is condensed into a blindingly bright searchlight, or aperture directly ahead. This is not merely a trick of the light, it is the consequence of catching up to the photons emitted by the universe. The familiar constellations of Earth would not just stretch, they would implode into a single point of brilliance, a starbow of intense radiation, ranging from gamma rays in the center to radio waves at the fringes. Navigating by visual reference becomes impossible. The pilot is no longer flying through a 3D void of scattered points. They are flying down a tunnel of light where the destination is the only visible thing, and it appears deceptively close. This deception of proximity is perhaps the most profound psychological impact of length contraction. In our terrestrial experience, distance is an obstacle to be overcome by effort. In a relativistic universe, distance is a variable to be overcome by energy. The more energy you pour into the system, acceleration, the physically smaller the universe becomes. It suggests that the cosmos does not have a fixed size. Its diameter is not a static number of light years, it is a function of how fast you're willing to go. To a photon, the universe has no width at all. It is born in a star and absorbed by an eye in the same instant, traversing zero distance. For a human traveller, this creates a God mode perspective on geography. If one could accelerate continuously at 1g, Earth's gravity, effectively simulating gravity while gaining speed, the galaxy itself would contract to the size of a neighbourhood after a few decades of ship time. The traveller could cross the 100,000 light-year span of the Milky Way in roughly 12 years of their own life. But this power comes with a heavy price, the isolation of the Lorentz factor. While the traveller enjoys the contracted universe, where planets are stepping stones and galaxies are mere islands, they are severing their causal connection to the rest of humanity. The contraction is private. It belongs only to the traveller. To the mission control back on Earth, the ship is not skipping across a shortened pond. It is crawling painfully slowly across the vast, uncontracted void. The traveller might radio back, "I'm halfway there, the distance is only 2 light years now." But the radio signal, travelling at light speed, traverses the uncontracted space. By the time the message reaches Earth, years have passed. The reality of the distance is fundamentally different for the two parties. One lives in a small, dense universe, the other lives in a vast, empty one. They no longer inhabit the same geometric reality. There is also the jarring phenomenon of deceleration. We often discuss the journey out, but the arrival is where the illusion shatters. As the spacecraft fires its retro rockets to slow down for Proxima Centauri, the Lorentz factor, run gamma Dalo, decreases. As our gamma Dalas drops back toward 1, space begins to relax and expand back to its proper length. Imagine the psychological shock for the pilot. For weeks, Proxima Centauri has appeared to be just a few astronomical units away, a stone's throw. It dominates the forward view, large and bright. But as the pilot hits the brakes, the universe inflates. The destination physically recedes. It moves away faster than the ship is slowing down, as the contracted miles spring back into existence. It is the reverse of a zoom lens. The pilot is slowing down, but the target is seemingly running away, creating a sensation of Zeno's paradox, where the harder you try to stop, the further the finish line appears to jump. This cosmic inflation at the end of the journey would be a disorienting, perhaps nauseating reminder that the traveller is returning to the slow, heavy, vast realm of non-relativistic physics. Furthermore, length contraction challenges our understanding of the shape of physical objects. We assume distinct shapes, spheres, cubes, pyramids, are intrinsic properties of matter. Relativity tells us that shape is an artifact of interaction. An electron, often modelled as a point or a probability cloud, behaves differently when moving at high speeds in a particle accelerator. It interacts with targets as if it were a flattened disk. This pancaking of subatomic particles is vital for the operation of colliders like the LHC. If length contraction were a myth, our particle physics would fail. We are essentially smashing relativistic pancakes together to see what crumbs fall out. Applying this to a macroscopic scale, if an alien civilization were to fly past Earth at 90% light speed, they would measure our planet not as a sphere, but as an oblate ellipsoid, squashed along the axis of their travel. They would measure the distance from New York to London as significantly shorter than we do. Their maps of Earth would be distorted compared to ours, yet perfectly accurate for their frame of reference. If they attempted to land, their deceleration would involve a complex transformation of coordinates, where our planet stretches back into a sphere as they match our velocity. This implies that there is no true map of the galaxy. There are infinite maps, each valid for a specific velocity vector. The ultimate extrapolation of length contraction brings us to the concept of the singularity of speed. As velocity approaches a certain ln, the speed of light, length approaches 0. At this theoretical limit, the third dimension in the direction of travel vanishes. The universe collapses into a two-dimensional plane. All galaxies, all stars, all history along that path are compressed into a single sheet of infinite density and 0 thickness. While matter with mass can never reach this state, the asymptote serves as a boundary condition for reality. It suggests that space is not a fundamental container, but a relationship generated by the separation of events in time. If you remove the time component by moving at thea zettalis, you remove the space component. In conclusion, length contraction is the mechanism by which the universe maintains the speed of light as the cosmic speed limit. It is the universe's way of balancing the books. If you try to cheat the speed limit by going faster, the universe simply moves the finish line closer. It allows the traveller to traverse the infinite, but only by shrinking the infinite down to a manageable size. This subjective shrinking is the only loophole we have for interstellar travel. We cannot make the galaxy smaller for everyone. but we can make it smaller for ourselves. The stars are not fixed in their positions. They're pinned to the fabric of space-time, and that fabric is elastic. For the relativistic voyager, the cosmos is a dynamic accordion, squeezing and stretching with the throttle of the starship. This realization changes the dream of space travel from a conquest of distance to a manipulation of geometry. We do not need to conquer the void. We need to contract it. And in doing so, we accept that the universe we explore will never be the same universe as the one we left behind. We are exploring a private, compressed reality, a pocket universe created by our own momentum, fleeting and fragile, existing only as long as we keep the engines burning. The famous equation E = mc2, perhaps the most recognized scientific formula in the world, encapsulates a profound truth. Mass and energy are interchangeable. They are two manifestations of the same fundamental entity. This equivalence has staggering implications for relativistic travel, particularly when considering the energy required for acceleration. As an object accelerates to speeds approaching that of light, its kinetic energy increases, but not in the simple Newtonian way. Instead, the object's effective mass, often called relativistic mass, also increases. This means that as a spacecraft approaches light speed, it effectively becomes heavier, requiring exponentially more energy to achieve each additional increment of velocity. This makes acceleration increasingly difficult, as if the universe itself were pushing back, resisting further increases in speed. The energy requirements for relativistic travel are truly immense. To accelerate even a small object to a significant fraction of light speed demands energy levels that dwarf current global power production. For example, accelerating a 1,000-kilogram spacecraft, roughly the mass of a small car, to 90% of the speed of light would require approximately 4.5 to 1019 joules of energy. To put that into perspective, this is equivalent to the energy released by about 1,000 large nuclear power plants operating for an entire year. And this is just for acceleration. Deceleration requires the same amount of energy. The rocket equation, which works so effectively for chemical propulsion, breaks down at relativistic speeds. In classical mechanics, the rocket equation relates the change in velocity to the exhaust velocity and the ratio of initial to final mass. However, at relativistic speeds, the effective mass of the rocket changes and the energy required to accelerate that mass becomes the dominant factor. The efficiency of converting fuel mass into kinetic energy becomes paramount, and traditional methods simply cannot provide the necessary power. The practical limitations of acceleration are not just about finding more powerful engines, they're about finding fundamentally new ways to generate and manage energy on a scale that is currently unimaginable. To surmount the tyranny of the rocket equation at relativistic speeds, we must look beyond the chemical bonds that power our current civilization and even beyond the nuclear fusion that powers the stars. The energy density of chemical fuel is pitifully low. Releasing the binding energy of electron shells yields only electron volts. Nuclear fission and fusion step this up to mega-electron volts, releasing a fraction of the mass energy stored in the nucleus, roughly 0.1% for fission and 0.7% for fusion. While this is an improvement of several orders of magnitude, it is still insufficient for the stars. To reach a Lorentz factor where time dilation becomes meaningful, a fusion-powered vessel would need to consist almost entirely of fuel, with a payload mass fraction so vanishingly small that the mission becomes pointless. The ship would essentially be a flying fuel tank the size of a moon, delivering a single probe the size of a toaster. The ultimate limit of energetic efficiency is matter-antimatter annihilation. This is the only known physical process that offers a theoretical 100% conversion of mass into energy. When a proton meets an antiproton, they annihilate, releasing their entire rest mass as high-energy gamma rays and short-lived particles called pions. A spacecraft powered by antimatter could, in theory, achieve relativistic velocities with a much more manageable mass ratio. However, the engineering challenges shift from generating energy to containing it. Antimatter is the most volatile substance in existence. It reacts instantly with any ordinary matter. Storing it requires magnetic traps, penning traps, inside a harsh vacuum, suspended by electromagnetic fields that must never fail. A microscopic leak in the containment system would result not in a fuel spill, but in a detonation equivalent to a thermonuclear warhead. Furthermore, production of antimatter is currently the most energy inefficient process on Earth. We spend billions of watts in particle accelerators to produce nanograms of antiprotons. To fuel a relativistic starship, we would need to manufacture tons of it, requiring a dedicated solar system-scale energy infrastructure. Even if we solve the fuel storage problem, we run into the waste heat catastrophe. In the vacuum of space, getting rid of heat is incredibly difficult because there is no air to conduct or convect it away. One can only radiate it as infrared light. A relativistic engine, even one that is 99% efficient, would still generate petawatts of waste heat. A single percent of the energy required to reach 0.9 C, if lost as heat within the ship's structure, would vaporize the vessel instantly. Consequently, a relativistic starship would likely look less like a sleek needle and more like a gigantic glowing radiator, huge gossamer wings of cooling fins extending for kilometers to dump the excess entropy of the engine into the cosmic background. The ship would shine brighter than the star it was leaving, a beacon of infrared radiation visible across the galaxy. This thermodynamic bottleneck forces us to reconsider the very concept of the rocket. The fundamental flaw of the rocket is that it must carry its own reaction mass. The faster you want to go, the more mass you need to expel, and therefore the more mass you must carry, which requires more energy to accelerate. This vicious cycle is broken only if the energy source is left behind. This leads to the concept of beamed propulsion, or beam riding. In this paradigm, the heavy machinery, the power plant and the accelerator remain stationary, perhaps orbiting the sun or built on the moon. It generates a collimated beam of photons, a massive laser, or microwaves. The spacecraft is equipped with a light sail, a mirror of immense surface area and negligible mass. The momentum of the beams striking the sail pushes the ship forward. Since the ship carries no fuel, it is not punished by the rocket equation. It can continue to accelerate as long as the beam is focused on it. The energy requirements are still astronomical, requiring a laser array with the power output of a Type 1 civilization. But the engineering is shifted from a fragile moving vessel to a stable non-moving platform. However, relativistic beam riding introduces the problem of diffraction. Over light years, even the tightest laser beam spreads out. To push a sail at Proxima Centauri, the laser aperture on Earth would need to be kilometers wide to keep the beam focused on the sail. Furthermore, there is the stopping problem. A beam rider has no engine to slow down. It would zip past its destination at 90% light speed. Proposals to solve this involve magnetic braking against the destination star's stellar wind, or detaching a section of the sail to reflect the laser beam back onto the main ship, a photon brake. But these are maneuvers of extreme complexity and risk. Another theoretical workaround for the energy problem is to harvest the medium itself. The Bussard ramjet, proposed in 1960, envisions a ship that uses a massive electromagnetic funnel, thousands of kilometers in diameter, to scoop up the diffuse hydrogen atoms of the interstellar medium. These atoms are then funneled into a fusion reactor to provide thrust. In theory, this gives the ship an infinite range. It gathers its fuel as it flies. However, relativity reveals a cruel irony here, the drag paradox. As the ship approaches relativistic speeds, the interstellar hydrogen hits the magnetic scoop at nearly the speed of light. The momentum transfer from these impacts acts as a brake. For the ramjet to work, the energy derived from fusing the hydrogen must exceed the kinetic energy lost by colliding with it. Modern calculations suggest that the proton-proton fusion cycle is too slow to overcome this drag. Unless we find a way to catalyze fusion instantly, or use a different reaction like CNO, a Bussard ramjet might act more like a parachute than a rocket at high velocities. We must also consider the kinetic energy trap of the destination. Let's assume a civilization manages to accelerate a ship to 0.99 C. The ship and its crew now possess a relativistic kinetic energy that makes them a planet-killing weapon. If the navigation fails and they impact a planet, the release of energy would be comparable to an asteroid strike or a barrage of antimatter bombs. Relativistic travel turns every vehicle into a potential weapon of mass destruction. This implies that any civilization capable of such travel must also possess infallible traffic control and navigation systems, or they risk annihilating their own colonies by accidental collision. This danger necessitates shielding not just for the ship, but for the destination. The shielding issue for the ship itself is equally critical. At 0.9c, the distinction between radiation and matter blurs. A single stationary grain of sand floating in deep space, relative to the ship, becomes a relativistic projectile. Impacting a speck of dust at that speed would release energy equivalent to a tactical nuclear explosion. The ship is essentially flying into a particle accelerator beam. To survive, the ship requires massive physical shielding, meters of ice or lead, or active electromagnetic deflectors. Maintaining these shields consumes a significant portion of the ship's energy budget, reducing the amount available for propulsion. The vacuum of space becomes a thick, abrasive medium that erodes the hull atom by atom. This erosion, or ablation, sets a hard speed limit. There is a velocity at which the energy required to deflect the interstellar medium exceeds the energy the ship can generate, creating a terminal velocity for interstellar travel that is well below the speed of light. Pushing the boundaries of physics further, some theorists propose the Kugelblitz drive. A Kugelblitz is a black hole formed not by the collapse of matter, but by the extreme concentration of energy, light. If we could focus enough lasers into a microscopic point to create a Schwarzschild radius, we would have a black hole. A black hole of the right size, atomateur scale, would radiate Hawking radiation at an incredible rate. It would be the ultimate battery, converting matter perfectly into radiation to drive a parabolic reflector. The ship would essentially be surfing on the edge of a contained singularity. The energy density is perfect, but the danger is absolute. If the containment fails, the black hole doesn't just explode, it consumes the ship or drifts away to eat a planet. Moreover, a Kugelblitz has a lifespan. It evaporates. The ship must feed it matter to keep it from exploding. As smaller black holes are hotter and more volatile, this creates a delicate balancing act of feeding a tame monster while riding its exhaust. Finally, we must confront the mass dilation of the crew itself. This means the faster you go, the stiffer the ship becomes in response to applied force. You can pour more energy into the engines, but the acceleration diminishes. You are fighting the asymptotic structure of spacetime. At 0.999c, pouring in more energy barely increases your speed. Instead, it increases your mass energy. You're effectively adding inertia to the universe. This leads to a philosophical realization about relativistic energy. The universe seems designed to keep us local. The energy barrier is not just a technological hurdle, it is a fundamental wall. The amount of energy required to send a single human to another star at relativistic speeds could power a utopian civilization on Earth for centuries. It forces a choice between expansion and sustainability. We can either burn the resources of a solar system to send a handful of seeds into the dark, or we can use that energy to cultivate a garden here. Unless, of course, we find a way to manipulate the metric of spacetime itself, the warp drive or Alcubierre metric. This bypasses the energy mass restriction by moving the space around the ship, rather than moving the ship through space. But even this solution requires negative energy, or exotic matter, which may not exist, and if it does, the energy requirements to create a warp bubble originally estimated to be greater than the mass of the visible universe. While recent refinements have brought this down to only the mass of Jupiter, it remains a testament to the sheer stubbornness of Einstein's speed limit. In conclusion, relativistic energy teaches us that speed is the most expensive commodity in the cosmos. The linear thinking of add more fuel, go faster, dies at the event horizon of the light speed barrier. The future of interstellar travel, if it involves matter moving through space, will likely not be a sprint, but a marathon of coasting, beaming, and surviving. We will have to become masters of high-energy physics, not just to build bombs or reactors, but to build the very vessels that carry us. We will have to learn to wield the power of stars, trap antimatter, and deflect the dust of the void, all while balancing on the razor's edge of the Lorentz factor, where energy, mass, and time twist into a single, formidable knot that guards the exit to the solar system. The theoretical possibility of relativistic travel, though permitted by physics, clashes violently with present-day engineering capabilities. Bridging this chasm demands propulsion concepts that transcend anything humanity has yet conceived. Theoretical designs for relativistic spacecraft often lean into the realm of science fiction, but are grounded in the known laws of physics. Nuclear propulsion offers a significant leap beyond chemical rockets. Systems like nuclear thermal rockets heat propellant using a nuclear reactor, expelling it at much higher velocities than chemical combustion. Even more advanced, nuclear pulse propulsion, famously studied under Project Orion in the 1950s and 60s, proposed using sequential nuclear detonations behind a massive pusher plate to propel a spacecraft. While controversial due to the use of nuclear bombs, calculations showed Orion could theoretically achieve speeds of a few % of light speed, far exceeding anything else at the time. However, even nuclear pulse propulsion falls short of truly relativistic velocities. For that, we turn to more exotic concepts like antimatter drives. Antimatter annihilation is the most efficient known energy release process, converting 100% of mass into energy, EMC2. An antimatter rocket would store antimatter, antiprotons and positrons, and allow it to annihilate with matter, producing gamma rays and other high-energy particles that could be directed for thrust. The energy density of antimatter is astronomical, offering the theoretical potential to reach significant fractions of light speed. The challenges, however, are immense. Producing antimatter in sufficient quantities is currently extraordinarily expensive and inefficient, and storing it safely for long durations is an unsolved engineering problem. Another class of theoretical propulsion involves external energy sources, freeing the spacecraft from the burden of carrying all its fuel. Magnetic sails, for example, could harness the plasma winds emanating from stars or even the interstellar medium itself, using large magnetic fields to generate thrust. More ambitiously, beamed energy propulsion envisions a powerful laser array, perhaps orbiting a star, firing a concentrated beam of light at a massive lightweight sail attached to a spacecraft. This light sail could then be pushed to relativistic velocities without ever consuming onboard fuel. The challenges here involve building planet-sized laser arrays, sails kilometers across, and maintaining precise beam alignment over interstellar distances. The infrastructure needed for relativistic travel extends far beyond just the spacecraft. It would require a monumental global or even solar system-wide effort to mine resources, construct orbital manufacturing facilities, generate and store vast amounts of energy, and develop advanced artificial intelligence for mission control and automation. The scale of such an undertaking would redefine humanity's technological and societal priorities, demanding sustained investment and cooperation across generations. Beyond the immense hurdles of propulsion lies an equally formidable adversary, the interstellar medium itself. In the vacuum of space, we tend to imagine a void, but at relativistic speeds, the void becomes a solid wall. Space is filled with hydrogen atoms, dust grains, and micrometeoroids. To a spacecraft travelling at 20% of the speed of light, a collision with a grain of sand carries the kinetic energy of a tactical nuclear weapon. Even the tenuous hydrogen gas that permeates the galaxy transforms into a relentless beam of high-energy radiation, bombarding the ship's hull with an intensity that would strip away atoms and degrade materials within days. Therefore, the engineering of a relativistic starship is largely an exercise in armour and shielding. Conventional physical plating is insufficient. The mass required to physically block these impacts would make acceleration impossible. Instead, engineers must look to active shielding systems. One proposed solution involves generating a massive magnetic field, essentially a miniature magnetosphere, to deflect charged particles, protons and electrons, before they strike the hull. For neutral particles and larger dust grains, the solution might involve a sacrificial shield, perhaps a thick layer of ice or a specialized foam at the prow of the ship, that is designed to be ablated, vaporized, and replenished over the decades-long journey. Some concepts even propose using high-powered lasers to detect and vaporize debris kilometers ahead of the ship, clearing a tunnel through the interstellar dust. Furthermore, the structural integrity of the vessel faces the challenge of G-force engineering. While the ship is coasting, weightlessness prevails, but the acceleration and deceleration phases present distinct problems. To reach relativistic speeds in a reasonable time frame, a ship might need to accelerate at 1 g, Earth gravity, continuously. This sounds manageable for humans, but it requires the ship's internal systems, its fluid dynamics, its cooling loops, its delicate quantum computers, to function flawlessly under constant thrust for years. If the propulsion system relies on pulse detonations, like Orion, or sudden laser impulses, the structural shock absorption becomes critical. The ship must be rigid enough to withstand the thrust, but flexible enough not to shatter under the vibrations of a nuclear heartbeat. The problem of braking is perhaps the most overlooked aspect of relativistic travel. it is mathematically easier to speed up than to slow down. If a ship rides a laser beam from Earth, it has no laser at the destination to slow it. It would zip past Proxima Centauri in mere minutes. To stop, the ship must either carry enough fuel to fire retro-rockets, reintroducing the tyranny of the rocket equation, or deploy a magnetic sail to drag against the stellar wind of the destination star. This mag-sail braking maneuver would take months or years, spiraling into the target system while shedding velocity. The engineering of such a sail, superconducting loops hundreds of kilometers wide, deployed autonomously after decades of dormancy, requires a level of material science reliability that currently does not exist. This brings us to the reliability crisis. A trip to a nearby star might take 40 to 100 years. In that time, on Earth, every piece of technology we own would degrade, rust, or become obsolete. A relativistic starship must be self-repairing. It cannot rely on spare parts from home. It requires an onboard industrial capability, 3D printers that can print other 3D printers, mining drones to harvest asteroids for raw materials if systems fail mid-journey, and an AI capable of diagnosing faults that human engineers haven't even predicted. The ship must be a closed-loop ecosystem, not just biologically, but mechanically. It must be a von Neumann machine in limited form, capable of maintaining its own existence against the entropy of the void. The human element introduces the most fragile component of all. If the ship is crude, the life support engineering must be absolute. We're talking about a biosphere that must recycle 100% of its water, oxygen, and nutrients with zero loss for decades. The failure of a single bacterial culture in the waste recycling system could doom the mission. Consequently, many relativistic engineering concepts favour the post-biological approach. Sending frozen embryos to be gestated by robots upon arrival, or sending digitised human consciousnesses, should such technology arise, removes the caloric and psychological needs of a living crew. A ship carrying data chips and DNA sequences can accelerate faster, withstand harder radiation, and sleep through the millennia if necessary. However, if we persist with the dream of a generation ship, a vessel where humans live, reproduce and die, the engineering expands into sociology. The ship must be large enough to prevent genetic bottlenecks, implying a population of at least several hundred, ideally thousands. This demands a vessel the size of a city, spinning to create artificial gravity. The hull becomes a landscape. The engineering challenge here is terraforming in a bottle. We must create a stable climate, a radiation-proof atmosphere, and a soil cycle inside a metal can hurtling through the dark. The energy required to keep a mini-sun, fusion lamp, burning to grow crops for a century is a significant fraction of the propulsion energy. Communication at relativistic speeds introduces the latency gap. As the ship moves further away, the time delay for messages increases. By the time they reach the nearest star, a message takes over 4 years to return to Earth. Real-time control is impossible. The ship must be autonomous. This necessitates the development of an artificial general intelligence, AGI, of a class far superior to our current large language models. This ship mind would need to be the captain, engineer, doctor, and diplomat. It would need to make split-second decisions about navigation hazards or first contact scenarios without phoning home. The engineering of such software is as critical as the antimatter containment. A software bug at 0.9 C is a death sentence. We must also consider the visual and navigational reality of relativistic flight. As the ship approaches the speed of light, the view outside changes due to relativistic aberration and Doppler shifting. Stars ahead turn blue, then violet, then shift into invisible X-rays and gamma rays. The view behind turns red and fades to black. The visible universe contracts into a blindingly bright searchlight directly ahead. Navigational sensors must be engineered to see in these shifted spectrums. They must lock onto pulsars or quasars that remain visible despite the distortion. The ship is flying blind to the naked eye, guided by instruments that translate the warp geometry of spacetime into a readable map. Beyond the standard relativistic concepts lies the realm of metric engineering, manipulating spacetime itself. While the Alcubierre warp drive is often dismissed as pure theory, the engineering path to it involves the manipulation of negative energy densities and the Casimir effect. If humanity can master the engineering of the quantum vacuum, we might bypass the speed limit entirely. This would require exotic matter, with negative mass, a substance that repulsive gravity. While we cannot build this yet, the mathematical frameworks exist. Engineering a warp bubble involves creating a ring of this exotic matter to contract space in front of the ship and expand it behind. The energy requirements, originally thought to be greater than the mass of the universe, have been refined in recent theoretical papers to merely the mass of a planet, and perhaps even less with specific geometric configurations. This suggests a distant future where engineering is not about pushing mass, but about sculpting geometry. Even without warp drives, the energy infrastructure for a conventional, relativistic beam-swarmed launch is a planetary undertaking. To launch a probe to Alpha Centauri using a laser sail might require a laser array roughly the size of Texas, or a collection of orbital mirrors spanning thousands of kilometers. This demands a Kardashev Type 1 civilization, one that can harness all the solar energy falling on its planet. The construction of such an array would likely be the largest engineering project in history, requiring space-based solar power stations, lunar mining for materials to avoid launching millions of tons from Earth's gravity well, and a global political consensus to direct that much power, enough to boil Earth's oceans, outward into the dark. This highlights that relativistic travel is not just an engineering problem, it is an economic and species-level evolutionary filter. It requires a civilization to invest a significant percentage of its GDP into a project that will not yield a return on investment for a century or more. It demands a transition from short-term profit thinking to cathedral thinking, where the builders of the foundation know they will never see the spire. The arrival phase poses the final engineering hurdle: autonomous exploration and manufacturing. Once the ship stops, it is on its own. It must deploy swarms of probes to analyze the target system. If it is a colonization mission, it must find a suitable rock, mine it, refine materials, and build a habitat before the humans, or embryos, wake up. This requires seed factories, compact automated industrial units capable of exponential self-replication. One landing pod must turn into a mine, which turns into a refinery, which turns into a city. This nanotechnology, or macroscopic self-assembly, is the bridge between the traveller and the new world. Without it, the crew arrives only to die on a barren rock. Ultimately, engineering the impossible is about mastering the extremes. We must master the extreme cold of cryonics, the extreme heat of antimatter, the extreme violence of relativistic impact, and the extreme duration of deep time. It is a test of whether intelligence can outsmart the limitations of its biological origins and the vast, indifferent distances of the cosmos. The rocket is just the shell. The true machine is the civilization that builds it, a society that has decided to extend its reach beyond the cradle of its birth, engineering not just a vehicle, but a future among the stars. The blueprints are being drawn in the minds of physicists today, but the steel will be poured by the grandchildren of our grandchildren in the orbital shipyards of a world we can barely imagine. Even if the engineering challenges of relativistic propulsion could be overcome, the journey itself would impose immense strains on the human body and mind. The biological effects of long-term space travel are already a concern for missions within our solar system, and these challenges would be magnified exponentially on interstellar voyages. Bone density loss, muscle atrophy, and cardiovascular deconditioning are well-documented problems in microgravity. While artificial gravity, perhaps generated by rotating sections of the spacecraft, could mitigate some of these issues, maintaining a constant 1G over decades would require massive, complex structures. Radiation protection at high speeds becomes a critical concern. Interstellar space is not empty. It is permeated by cosmic rays, high-energy particles from distant supernovae and other astronomical phenomena. At relativistic velocities, the spacecraft itself would also be bombarded by hydrogen atoms from the interstellar medium, which would strike with the energy of cosmic rays. Shielding against this relentless barrage would require either massive physical barriers, adding enormous mass to the spacecraft, or advanced active shielding such as powerful magnetic fields to deflect charged particles. The long-term exposure to even low levels of radiation could significantly increase cancer risk and genetic damage. The psychological challenges of extended missions, potentially spanning decades or even centuries in Earth time, are profound. Crew members would be living in an artificial environment, isolated from Earth and all familiar human contact. Monotony, confinement, and the sheer scale of the journey could lead to severe psychological distress. Maintaining mental health and social cohesion among a small group of individuals over such vast periods would require sophisticated psychological support systems, robust crew selection processes, and perhaps even advanced forms of virtual reality or simulated environments to provide a sense of normalcy and connection. Life support systems for decades-long voyages would need to be entirely self-sustaining closed-loop ecosystems. Recycling air, water, and waste with near-perfect efficiency, growing food, and maintaining a stable internal environment would be paramount. Any failure in these systems could be catastrophic, as resupply from Earth would be impossible. These systems would need to be incredibly robust, redundant, and capable of self-repair, operating flawlessly for generations. The human element, fragile and demanding, remains one of the most formidable barriers to long-duration relativistic space travel. The theoretical framework of time dilation finds its most compelling application in the context of relativistic space travel, creating a stark divergence between Earth time and ship time. For a crew embarking on an interstellar voyage at speeds approaching light, the passage of time on their spacecraft would slow down relative to Earth. This means that while decades or even centuries might pass for those remaining on Earth, the travellers themselves would experience only years or even months. Consider a journey to a star 50 light-years away. If a spacecraft could achieve 99% of the speed of light, the journey would take approximately 50.5 years in Earth time. However, due to time dilation, the crew aboard the spacecraft would experience only about 7.1 years passing. This means they could complete the round trip, spending around 14.2 years of their subjective lives, while over a century would have elapsed on Earth. This radical difference in experience time creates unique communication challenges. A message sent from the spacecraft during the first year of its journey would take nearly 50 years to reach Earth. Any reply would take another 50 years to return, arriving long after the travellers had reached their destination. Real-time conversation across light years becomes impossible, replaced by a slow, asynchronous exchange of historical data. The social implications of this time differential are immense. Travellers returning to Earth would find a world profoundly changed, perhaps beyond recognition. Their families, friends, and entire societies would have aged or passed away across generations. They would be living artifacts from a bygone era, potentially struggling to integrate into a future that has evolved for centuries without them. This creates a profound sense of temporal isolation. Planning missions with multiple reference frames requires a complete rethinking of mission objectives and crew psychology. Travellers would need to fully grasp that they are undertaking a one-way journey into the future of their home planet. The mission might be framed not as a return to the past, but as a commitment to the exploration of the future. The data they collect, the experiences they gain, and the knowledge they bring back would be for future generations, not for the society they left behind. This temporal disconnect transforms the very nature of exploration, making it a profound act of self-sacrifice for the advancement of future humanity. Mapping what's accessible within a human lifetime, accounting for time dilation, transforms our understanding of cosmic distances. The universe, from the perspective of a relativistic traveller, effectively shrinks. The critical factor is not just maximum speed, but also the rate of acceleration, as achieving relativistic velocities takes time and energy. A spacecraft that can accelerate continuously at 1g, Earth's gravity, would reach significant relativistic speeds relatively quickly. For instance, after about a year of continuous 1g acceleration, a spacecraft would be travelling at roughly 77% of the speed of light, with a gamma factor of about 1.6. However, maintaining continuous acceleration requires immense and sustained power, pushing the limits of even theoretical propulsion systems. The maximum practical speeds, therefore, become a trade-off between energy expenditure, engineering feasibility, and the desired time dilation effect. Even at 99.9% of light speed, where the gamma factor is approximately 22.36, a significant portion of the Milky Way galaxy could be explored within a few decades of ship time. Potential destinations within 50 years of ship time, from the traveller's perspective, could extend to many thousands of light years. For example, at a gamma factor of 1000, meaning 1 year of ship time equals 1000 years of Earth time, a journey of 50,000 light years could be completed in 50 years of subjective time. This brings the galactic centre, with its supermassive black hole and dense starfields within reach. Even other galaxies like the Magellanic Clouds could become destinations. The concept of light cones and causality provides a fundamental boundary to what can be reached. A light cone represents the path that light, and therefore information, can take from a given event. For any event, there is a future light cone containing all events that can be influenced by it, and a past light cone containing all events that could have influenced it. Relativistic travel allows a traveller to extend their personal light cone further into the universe, but it cannot allow them to travel outside the fundamental boundaries of causality. They cannot travel faster than light, nor can they reach destinations that were already outside their past light cone at the moment of departure. The reachable universe, while expanded by time dilation, remains constrained by the immutable laws of spacetime. Even with the most advanced relativistic propulsion, the universe itself imposes ultimate limits on human travel, largely due to its expansion and the mysterious force known as dark energy. The universe is not a static entity. It is actively growing, with galaxies receding from one another, much like raisins in a rising loaf of bread. This expansion, discovered by Edwin Hubble and later confirmed to be accelerating due to dark energy, profoundly affects what we can ever hope to reach. Dark energy, a pervasive and enigmatic force, is causing the expansion of the universe to speed up. This means that distant galaxies are not only moving away from us, but their recession velocity is increasing over time. This accelerated expansion creates a cosmic event horizon, a boundary beyond which light from distant objects will never be able to reach us, even if emitted today. Conversely, it defines regions that we can never reach, regardless of how fast we travel. Even if a spacecraft could travel at 99% of light speed, destinations beyond approximately 17 billion light-years in our current epoch will remain forever inaccessible. Accelerating towards them merely postpones the inevitable moment when the expansion of space carries them beyond our reach. This means there are places we can never reach, no matter how fast we go. The cosmic event horizon is not a physical barrier, but a consequence of the expanding spacetime. Any object beyond this horizon is receding from us faster than the speed of light due to the expansion of space itself. While no object can move through space faster than light, space itself can expand at any rate. Moreover, the observable universe, the sphere of all matter whose light has had time to reach us, is not static either. While its physical size increases, the number of galaxies within it that are currently observable is shrinking. As galaxies cross the cosmic event horizon due to accelerated expansion, their light becomes unable to reach us. This means that during a long, relativistic journey, destinations that were initially within our reach might cross this horizon and become permanently inaccessible. The accessible universe shrinks even as travelers attempt to explore it, imposing a kind of ultimate deadline on cosmic exploration. The social and psychological implications of one-way trips, inherent in highly relativistic travel, are profound and transformative. A traveller departing on such a journey accepts permanent exile, not just from their home planet, but from their entire historical era. Time dilation ensures that even if they return, the Earth they left behind will have aged by centuries, millennia, or even millions of years. This severs the fundamental human connection to one's past. The impossibility of maintaining real-time contact exacerbates this isolation. Communication will be a one-way stream of historical data from Earth and a slow, delayed trickle of observations from the spacecraft. There will be no possibility of immediate dialogue, no comforting back and forth. This absence of living connection will inevitably lead to a profound sense of loneliness and detachment. Cultural evolution during long voyages would see the crew develop their own distinct culture, traditions, and even language, diverging from the Earth they left behind. Over generations, a generation ship or a series of relativistic missions would create entirely new human societies, distinct from their terrestrial origins. This raises questions about the continuity of human identity and what it means to be human when separated by such vast gulfs of space and time. The question of colonization versus exploration becomes central. Is the goal to establish new outposts of humanity, or simply to observe and return data? If colonization is the aim, the new colony would be entirely independent, with no practical ties to the homeworld. If exploration is the goal, the returning explorers would be living anachronisms, bringing back data to a world that might no longer understand or value it in the same way. The philosophical implications of leaving Earth forever are immense. It forces humanity to confront its place in the cosmos, the value of connection versus discovery, and the ultimate purpose of our existence. Is it our destiny to spread throughout the stars, even if it means fragmenting into countless isolated civilizations? Or is our collective identity tied to our shared history on Earth? Relativistic travel forces a reckoning with these fundamental questions, defining the ultimate cost of distance. A detailed mission profile for reaching Alpha Centauri, our nearest stellar neighbour at approximately 437 light-years away, provides a concrete example of relativistic travel's challenges and rewards. Assuming a propulsion system capable of sustained acceleration, perhaps an advanced antimatter drive or a powerful beamed energy system, a mission could be designed to reach this system within a human lifetime. Time dilation effects would be crucial for this journey. At 90% of light speed, a one-way trip to Alpha Centauri would take about 4.85 years of ship time, while approximately 4.85 years. Gamma, 2.29. Wang, 11.1 years would pass on Earth. A round trip at this speed would mean the travellers experience about 9.7 years, but Earth would age 22.2 years. To make the journey even shorter for the crew, say 1 year one way, would require a much higher velocity, around 99.5% of light speed, where gamma is about 10. Earth would age 4.37, 10, young 43.7 years during this one-way trip. Communication and monitoring strategies would be complex. Messages from Earth would take 4.37 years to reach the spacecraft, and replies would take another 4.37 years to return. This means any conversation would span nearly a decade. Continuous monitoring of the spacecraft's health, trajectory and crew well-being would be essential, relying on highly autonomous systems and robust, long-range communication arrays. The resource requirements and engineering challenges for such a mission are staggering. The spacecraft itself would need to be a self-contained ecosystem, providing life support for years, radiation shielding and propulsion for both acceleration and deceleration. The energy required to accelerate a human-carrying vessel to 99.5% of light speed would be enormous, likely requiring a facility capable of generating and storing energy on a planetary scale. Despite the immense difficulties, the potential scientific returns would be revolutionary. Alpha Centauri is a triple-star system, with Alpha Centauri A and B, Sun-like stars, and Proxima Centauri, a red dwarf known to host an exoplanet Proxima Centauri b in its habitable zone. Direct observation and perhaps even robotic probes dispatched from the human mission could provide unprecedented data on these worlds, potentially revealing signs of life or even an alien biosphere. The knowledge gained would fundamentally alter our understanding of planetary formation, stellar evolution, and the prevalence of life in the universe. Crossing the Milky Way galaxy, a vast spiral spanning approximately 100,000 light-years, presents an entirely different scale of challenge compared to reaching a nearby star. Even with highly relativistic travel, such a journey would push the limits of human endurance and technological capability. Routes through the Milky Way would likely involve navigating through dense star fields, avoiding active galactic nuclei, and potentially utilizing gravitational assists from massive objects, though the latter would be complex at relativistic speeds. Notable destinations could include star-forming regions, globular clusters, or even the galactic core, a region of immense gravitational forces and a supermassive black hole. The accessibility of these destinations would be entirely dependent on the achievable gamma factor. Navigation challenges at relativistic speeds are profound. The apparent positions of stars shift due to relativistic aberration, and the cosmic microwave background radiation would be blue-shifted into a blinding, deadly wall of X-rays and gamma rays ahead of the spacecraft. Automated navigation systems, perhaps guided by advanced AI, would need to interpret this distorted view of the cosmos and plot a course with extreme precision over millennia of Earth time. Interaction with the interstellar medium, though sparse, becomes a significant hazard at relativistic velocities. Even a few hydrogen atoms per cubic centimetre, when struck at 99.99% of light speed, deliver energies equivalent to cosmic rays, creating a continuous bombardment that demands unprecedented shielding. Dust grains, though rare, could become catastrophic projectiles. The time requirements for various missions would be dictated by the desired subjective duration for the travellers. A journey across the entire 100,000 light-year span of the galaxy, at a gamma factor of 1,000, meaning 1 year ship time, so 1,000 years Earth time, would still take 100 years of subjective time for the crew. Earth, however, would age 100 million years during this single journey. This emphasises that crossing the galaxy within a human lifetime, even a subjectively extended one, means utterly severing ties with the home civilization, which would likely be long gone or utterly transformed upon any return. Could humans ever reach another galaxy, such as Andromeda, our closest large galactic neighbour, located approximately 2.5 million light-years away? The sheer scale of this distance makes it the ultimate test of relativistic travel, pushing the boundaries of what is even theoretically possible within a human lifetime. Time dilation effects at these extreme distances become the only mechanism that makes such a journey conceivable for biological beings. To cross 2.5 million light-years within, say, 50 years of subjective ship time would require an extraordinary gamma factor of 50,000. This means travelling at a speed so infinitesimally close to light speed that the difference is measured in fractions of a percent, many nines after the decimal point. For every year the travellers experience, 50,000 years would pass on Earth. During a 50-year journey, Earth would age 2.5 million years, returning to an era far beyond anything recognisable. The role of the intergalactic medium, while even sparser than the interstellar medium, still presents hazards. Over millions of light-years, the cumulative effect of even tiny amounts of hydrogen and dust, striking at extreme relativistic velocities, would be significant. Shielding requirements would be monumental, demanding technologies far beyond even our theoretical current imaginings. Planning multi-million light-year journeys would require unprecedented foresight and technological capability. It would be a one-way trip in the most absolute sense, with no possibility of communication or return to the original civilization. These would be voyages of ultimate exploration, planting seeds of humanity in a new galaxy, or simply observing the cosmos from an unimaginable vantage point. Arrival scenarios and timing would be critical. Deceleration would need to be precisely managed over vast distances to avoid overshooting the target galaxy or colliding with intergalactic debris. The travellers would arrive in Andromeda to find a galaxy that has evolved for 2.5 million years since the light they observed at their departure left that galaxy. They would witness the present-day Andromeda, a breathtaking spectacle, but one that has changed dramatically from the ancient light that guided their journey. The Andromeda option represents the ultimate frontier of human exploration, a journey not just across space, but across unimaginable stretches of cosmic time. The pursuit of interstellar travel, particularly at relativistic speeds, is not a monolithic endeavour. It encompasses multiple potential paths, each with its own trade-offs between speed, distance, and the survival of the human element. Comparing different mission profiles highlights these trade-offs. A slow, multi-generational ship travelling at sublight speeds, perhaps 1% or 2% of light speed, would allow a continuous human presence, with generations born and dying on board before reaching their destination. This approach maintains a cultural continuity for the travellers, but severs ties with Earth even more completely, as the original crew would be long dead upon arrival. Relativistic travel, by contrast, allows the original crew to reach the destination within a subjective lifetime, but severs their connection to Earth's timeline. The trade-offs between speed and distance are stark. Low speeds mean longer Earth-time journeys, but less extreme technological demands. Higher speeds mean shorter subjective journey times, but require exponentially more energy and engineering prowess. The choice depends on the ultimate goal: rapid exploration by a few individuals versus gradual large-scale colonization. The role of generation ships versus relativistic travel represents two fundamentally different philosophies. Generation ships prioritize the preservation of a human society during the journey, accepting the immense Earth-time duration. Relativistic travel prioritizes the individual traveler's subjective experience, allowing them to witness distant stars within their lifespan, but at the cost of temporal isolation from Earth. Hybrid approaches to long-distance travel might combine elements of both. Perhaps a relativistic scout ship could reach a distant star system quickly, followed by slower generation ships carrying colonists once a suitable destination is identified. Or a relativistic ship could carry frozen embryos or genetic material to be thawed and raised by AI upon arrival, combining speed with the potential for long-term colonization. Risk assessment for different strategies is crucial. Generation ships face risks of social breakdown, resource depletion, and biological degradation over centuries. Relativistic ships face extreme technological demands, radiation hazards, and the profound psychological impact of temporal displacement. Each path carries immense stakes, demanding careful consideration of not just engineering, but also sociological and ethical implications. Achieving relativistic travel demands a series of technical breakthroughs that fundamentally redefine our technological capabilities. The propulsion system requirements are paramount. Current chemical rockets are insufficient by orders of magnitude. Theoretical concepts like antimatter drives, fusion rockets, or beamed energy propulsion offer promise, but remain largely in the realm of theoretical physics or early-stage research. Such systems require unprecedented energy generation, storage, and conversion efficiencies far beyond anything currently in existence. Navigation at relativistic speeds presents unique challenges. The universe appears distorted due to relativistic aberration and blue shifting, making traditional celestial navigation impossible. Advanced autonomous navigation systems, potentially employing AI and real-time spacetime mapping, would be necessary to plot a course and avoid interstellar hazards. The precision required to hit a target star system light-years away while moving at near-light speed is staggering. Shielding from interstellar radiation is a critical safety concern. At relativistic velocities, hydrogen atoms in the interstellar medium become high-energy projectiles, and cosmic rays become even more dangerous. Passive shielding using dense materials quickly becomes prohibitively massive. Active shielding, such as powerful magnetic fields to deflect charged particles, would require immense power and advanced materials science to create and maintain. The long-term effects of even residual radiation on biological systems remain a major unknown. Communication systems across light years would operate under the constraints of light speed delay. High-gain directional antennas, powerful transmitters, and advanced error correction protocols would be needed to send and receive data across vast distances. The asynchronous nature of communication means that a slow, deliberate exchange of information would replace real-time interaction. Emergency scenarios and backup systems would need to be incredibly robust and self-sufficient. Resupply or rescue missions would be impossible from Earth. The spacecraft must be designed to withstand catastrophic failures, perform complex repairs autonomously, and ensure the survival of its crew for decades without external assistance. This level of self-reliance pushes the boundaries of engineering and robotics. The prospect of relativistic travel, with its inherent time dilation and isolation, forces humanity to confront profound philosophical questions about our place in the cosmos and the nature of existence. The meaning of time at cosmic scales becomes fluid. Our human perception of time as a linear absolute progression dissolves, replaced by a relativistic understanding where different observers experience different durations. This challenges our very concept of history and future. Questions of human identity and continuity are central. If a traveller returns to an Earth millions of years in its future, are they still connected to the humanity they left behind? Does their identity remain intact? Or are they a new species of temporal exile? What constitutes human continuity across such vast temporal divides? These questions probe the very essence of what it means to be human. Ethical considerations of one-way missions are immense. Is it ethical to send individuals on a journey from which they can never truly return to their past? What are the psychological and social responsibilities we bear towards such voyages? The decision to embark on such a mission would represent a profound commitment, demanding a re-evaluation of our moral framework concerning long-duration spaceflight. The purpose of human space exploration itself comes into question. Is it to expand our territory, to seek out new knowledge, or to ensure the survival of our species? If the cost is the permanent fragmentation of human civilization across time and space, is it a price worth paying? Relativistic travel elevates exploration from a scientific endeavour to an existential one. Finally, the legacy of relativistic travelers would be unique. They would not just be explorers, they would be living bridges to a distant past, or perhaps the progenitors of entirely new branches of human civilization. Their journey would redefine what it means to leave a mark on the universe, transforming not just space, but time itself. While relativistic travel remains a distant dream, theoretical breakthroughs and future technologies could significantly alter its feasibility. Quantum propulsion possibilities, though highly speculative, represent a realm beyond current physics. Concepts like warp drives, which would manipulate spacetime itself to effectively shorten distances, or wormholes, which could create shortcuts through spacetime, are often discussed. While the mathematics for these concepts exists, the energy requirements and the ability to control spacetime are currently beyond our grasp. Some quantum field theory calculations suggest that small amounts of negative energy density might be achievable through quantum effects, but scaling these to stabilize a macroscopic wormhole is entirely speculative. Even if wormholes could be created, transporting one mouth to a distant star at conventional velocities before establishing a shortcut still requires solving the propulsion problems they were supposed to bypass. Revolutionary energy sources are perhaps the most critical component. Advanced fusion power, harnessing the same process that powers stars, could provide immense energy, potentially propelling spacecraft to 15 to 20% of light speed. Beyond fusion, entirely new methods of energy extraction, perhaps tapping into vacuum energy or black hole accretion disks, would be needed for truly relativistic velocities. Advanced materials and their applications would be essential. Super-strong, lightweight materials capable of withstanding extreme stresses and radiation would be needed for spacecraft hulls and shielding. Self-repairing materials, nanotechnology, and metamaterials could revolutionize spacecraft design, making vessels more robust and adaptable to the harsh interstellar environment. The role of artificial intelligence in space travel would be transformative. AI could manage complex propulsion systems, navigate through distorted spacetime, monitor and maintain life support, and even provide psychological support for human crews. For multi-generational journeys, AI might even be responsible for raising future generations of travelers, acting as surrogate parents and educators. AI could also oversee autonomous probes dispatched from relativistic ships, further extending the reach of human exploration. Even with perfect propulsion, the universe itself imposes ultimate physical boundaries that cannot be crossed, defining humanity's ultimate reach into space. The final barrier of light speed remains immutable for any object with mass. One can approach it, adding more nines to the percentage, but never quite reach it due to the infinite energy requirement. This means that while time dilation can drastically reduce subjective journey times, it cannot eliminate them entirely. Universal expansion and its consequences represent another fundamental limit. As dark energy accelerates the expansion of space, distant galaxies recede from us faster than light. This creates a cosmic event horizon, beyond which no signal or traveller can ever reach us, even if they could travel at light speed. The universe is not merely vast, it is actively pulling itself apart, making some regions forever inaccessible. The largest possible journey, therefore, is not the entire universe, but rather the portion of the universe that lies within our cosmic event horizon. Even this accessible region is shrinking as the expansion accelerates. A traveller might embark towards a galaxy that is currently within reach, only to find that during their decades-long relativistic journey, the expansion of space has carried their destination beyond their event horizon, rendering it permanently inaccessible. Humanity's ultimate reach into space is thus not solely determined by our technological prowess, but by the fundamental laws of physics and the dynamic nature of the cosmos itself. While time dilation offers a path to traverse immense distances within a human lifetime, the expanding universe ultimately sets a deadline, defining the true, uncrossable boundaries of our cosmic journey. This cosmic horizon is not a physical barrier in the traditional sense, like a wall or a fence. Instead, it is a boundary of information, a limit beyond which light from distant objects can no longer reach us, and consequently, we can no longer reach them. It is a consequence of the universe's relentless expansion, an expansion that is not merely stretching the fabric of space, but accelerating, pushing galaxies further and further apart at an ever-increasing rate. Consider the implications of this accelerating expansion on a journey spanning light years. Imagine a hypothetical starship, a marvel of future engineering, capable of sustaining its crew for generations and propelling itself to a significant fraction of the speed of light. Its mission might be to reach a distant, habitable exoplanet in a galaxy millions of light years away. For the crew aboard this vessel, time would slow down relative to those left behind on Earth, a phenomenon known as time dilation. This means that while decades might pass for the astronauts, centuries or even millennia could elapse on their home planet. This relativistic effect is what makes interstellar and even intergalactic travel within a human lifespan theoretically possible, as it compresses the subjective duration of the journey for the travellers. However, the universe plays a cruel trick. As the starship hurtles through space, the very fabric of the cosmos between it and its destination is stretching. This stretching is not uniform, it is accelerating. The further away the destination, the more pronounced this effect becomes. What might have appeared as a reachable target at the outset of the journey could, by the time the starship has covered a substantial portion of the distance, have receded beyond the cosmic event horizon. This is not because the starship is slowing down, or because the destination is actively moving away from it in the conventional sense. Rather, the space itself between the starship and its target is expanding so rapidly that the rate at which distance is being created outstrips the starship's ability to cover that distance. It's like trying to walk to a point on an infinitely stretching rubber band. No matter how fast you walk, the point keeps getting further away because the band itself is getting longer. This concept of a shrinking accessible universe is profoundly counterintuitive, especially when we are accustomed to thinking of space as a static, unchanging arena. But the universe is anything but static. It is a dynamic, evolving entity, and its expansion is the dominant force shaping the ultimate limits of our exploration. Even if we could instantaneously jump to a galaxy currently within our observable universe, the accelerating expansion means that over time, the light from that galaxy would eventually redshift beyond detection, and it would effectively disappear from our observable horizon. For a traveller, this means that even if they reach such a distant galaxy, the ability to communicate with or even observe their home galaxy, the Milky Way, would eventually be lost. The universe would become a series of isolated islands, each an expanding bubble of observable space, with no way to bridge the ever-growing voids between them. The cosmic event horizon, therefore, represents a fundamental boundary that no amount of technological advancement, no matter how sophisticated, can overcome. It is a boundary imposed by the very nature of spacetime and its expansion. While time dilation can extend the subjective lifespan of a traveller and allow them to experience vast distances in a compressed time frame, it cannot circumvent the fact that certain regions of the universe are simply moving away from us faster than light can traverse the intervening space. This isn't a limitation of our propulsion systems, it's a limitation of causality itself. Information, and therefore any physical object, cannot travel faster than light. If the space between us and a distant galaxy is expanding at a rate that pushes that galaxy away from us faster than light can cover the distance, then that galaxy becomes forever unreachable. This realization paints a somewhat melancholic picture of humanity's long-term cosmic destiny. While we might dream of a future where we colonize countless star systems across multiple galaxies, the accelerating expansion of the universe suggests that our reach is ultimately finite. The observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang, is constantly expanding. However, the causally connected universe, the region from which we can ever hope to receive information or send a probe, is actually shrinking in terms of what we can ultimately interact with. The galaxies that are currently just within our cosmic event horizon are already on their way out, destined to become isolated from us in the distant future. Consider the implications for interstellar communication. Even if we could send a signal to a distant civilization, the return message might never reach us if their galaxy crosses our event horizon before the signal completes its journey. This makes long-term intergalactic communication a race against cosmic expansion, a race that the expansion is ultimately destined to win. The universe is not just vast, it is actively working to isolate its constituent parts, pushing them further and further into cosmic solitude. The concept of a traveller embarking on a multi-generational mission, only to find their destination has receded beyond reach, is a powerful illustration of this cosmic dynamic. Imagine the sheer dedication, the immense resources and the profound hope invested in such a journey. Generations might be born and die aboard the starship, their entire existence defined by the pursuit of a distant star. Yet, upon arrival, or perhaps even before, the realization dawns that the target world is no longer truly reachable. The light from it might still be visible, but the space between has stretched so immensely that the journey would now take an effectively infinite amount of time, or more accurately, the destination is receding faster than the starship can ever hope to catch up. This isn't a scenario where better engines or more efficient fuel could solve the problem. It's a fundamental consequence of the cosmological constant, the mysterious force believed to be responsible for the accelerating expansion of the universe. This constant, often associated with dark energy, dictates the ultimate fate of the cosmos, and by extension, the ultimate limits of our ability to traverse it. Without a fundamental shift in our understanding of physics, or perhaps a revolutionary discovery that allows us to manipulate spacetime itself in ways we currently deem impossible, the cosmic event horizon will remain an unyielding barrier. The human impulse to explore, to push boundaries, is deeply ingrained. From the earliest hominids venturing beyond their immediate surroundings to the sailors crossing vast oceans, and now to the engineers designing rockets to reach other planets, the desire to see what lies beyond has driven our species forward. But in the grand cosmic scheme, there exists a boundary that even this indomitable spirit cannot overcome. The universe, in its majestic indifference, imposes limits that are not merely technological, but existential. This does not mean that interstellar travel within our own galaxy is impossible. Within the Milky Way, the expansion of space is largely overcome by the gravitational forces binding stars and gas together. Our galaxy, and indeed our local group of galaxies, are gravitationally bound systems, meaning they are not expanding away from each other due to the cosmological expansion. Therefore, journeys to nearby stars within our galaxy remain theoretically feasible, assuming we can overcome the immense technological hurdles of propulsion, life support, and radiation shielding. But even within the Milky Way, the distances are staggering, requiring relativistic speeds and the accompanying time dilation to make such journeys viable within a human lifetime. The true significance of the cosmic event horizon lies in its implication for intergalactic travel. While we can currently observe galaxies billions of light years away, these are the galaxies that were much closer to us in the past, and whose light has only now reached us. Many of these distant galaxies are already receding from us at speeds greater than the speed of light due to the expansion of space. This is not a violation of Einstein's theory of special relativity, which states that nothing can move through space faster than light. Rather, it is the space itself that is expanding, carrying these galaxies along with it. The distinction is crucial. Imagine ants walking on an expanding balloon. The ants themselves might be walking slowly, but if the balloon inflates quickly enough, the distance between two ants can increase at a rate faster than either ant can traverse it, even if they are walking towards each other. Similarly, galaxies are not moving through space faster than light. Rather, the space between them is stretching, causing their relative distance to increase at superluminal rates. This means that for many distant galaxies, even if we were to embark on a journey towards them today, we would never arrive. They are already beyond our causal reach. This understanding forces us to confront the ultimate limitations of our cosmic journey. While the dream of exploring the entire universe is a romantic one, the reality is that our accessible universe is a finite and shrinking bubble. The universe is not a static canvas upon which we can paint our explorations. It is a living, breathing entity, constantly evolving, and its evolution dictates the boundaries of our reach. The accelerating expansion acts as a cosmic speed limit, not on our rockets, but on the very possibility of reaching certain destinations. The universe, in its vastness and dynamic nature, presents us with a profound paradox. The very forces that brought it into being and shaped its evolution are also the forces that will ultimately limit our ability to explore it fully. Dark energy, the mysterious component driving the accelerating expansion, is the ultimate gatekeeper, setting the final, uncrossable boundaries of our cosmic journey. It means that while the stars and galaxies we see today might seem like potential future destinations, many of them are already, in a very real sense, lost to us forever. Their light might still reach us, a ghostly echo of their past, but their future interaction with us is cosmically foreclosed. This understanding profoundly reshapes our perspective on the future of space exploration. It emphasizes the importance of exploring our own galactic neighborhood, the Milky Way, which remains gravitationally bound and thus accessible. The stars and exoplanets within our galaxy represent billions of potential destinations, more than enough to occupy humanity for countless millennia. However, the dream of intergalactic empires, of spanning the vast voids between galaxies, appears to be a fantasy ultimately thwarted by the fundamental laws of cosmology. The human lifespan, even when stretched by time dilation, is still a finite duration within the cosmic timescale. The accelerating expansion of the universe means that the window of opportunity for reaching certain distant objects is not infinite. It is a closing window. As time progresses, more and more galaxies will cross our cosmic event horizon, becoming permanently inaccessible. This gives a sense of urgency to our exploration, a recognition that the universe we observe today is not the universe that will always be accessible. The profound beauty of this realization lies in its humbling power. It reminds us that despite our technological advancements and our boundless ambition, we're ultimately subject to the grand, overarching laws of the cosmos. The universe does not bend to our will. Rather, we must understand and adapt to its immutable principles. The cosmic event horizon is not a defeat. It is a definition, a clarification of the true scope of our potential journey. It tells us that while the universe is unimaginably vast, our ability to traverse it, even with the most advanced technology imaginable, is ultimately bounded by the very fabric of space-time itself. This boundary is not a limit to our curiosity or our imagination, but a limit to our physical reach, a cosmic truth that shapes our destiny among the stars. The cosmic event horizon, then, is not merely an abstract astronomical concept. It is a profound philosophical statement about our place in the universe. It forces us to confront the transient nature of existence, both on a personal and a cosmic scale. Imagine a future civilization, perhaps millennia from now, looking out at a night sky far emptier than our own. The distant galaxies that currently fill our telescopes, shimmering with the light of billions of stars, would have receded beyond their observable universe, their light forever unable to reach them. This is not a scenario born of science fiction, but a scientifically predicted outcome of an accelerating universe. The expansion of space acts like a cosmic conveyor belt, carrying distant objects away from us at ever-increasing speeds. Eventually, the speed at which these objects recede will exceed the speed of light itself, not because the objects are moving through space faster than light, but because the space between us and them is expanding so rapidly. This phenomenon is often misunderstood, leading to the erroneous conclusion that objects are breaking the cosmic speed limit. Instead, it is the fabric of space itself that is stretching, increasing the distance between us and these far-flung galaxies faster than light can traverse that expanding void. For any future civilization, or even for us if we were to wait long enough, these galaxies would simply vanish from view, their light redshifted into oblivion, their presence erased from the observable cosmos. This impending cosmic isolation underscores the preciousness of our current observational window. We live in a unique epoch, a cosmic sweet spot where the universe is old enough for complex structures like galaxies and stars to have formed, yet young enough that a vast tapestry of these structures remains within our reach. To squander this opportunity, to fail to explore and understand this accessible universe, would be a profound oversight, a missed chance at comprehending the true grandeur of our cosmic home before it begins to fade. Consider the implications for interstellar travel. Even if we developed propulsion systems capable of approaching a significant fraction of the speed of light, the cosmic event horizon would still impose a fundamental limitation. Any destination beyond this horizon would be forever out of reach, regardless of how fast we could travel. It's like being on a ship in a rapidly flowing river, trying to reach a point upstream that is moving away from you faster than your ship can possibly go, even if your ship itself is incredibly fast. The current of the expanding universe is simply too strong. This realization reframes our understanding of space exploration. It shifts our focus from an infinite frontier to a vast yet ultimately bounded domain. Our efforts, therefore, should be concentrated on exploring and understanding the portion of the universe that is, and will remain, accessible to us. This involves not just our own galaxy, the Milky Way, but also the galaxies within our local group, and perhaps even some of the closer galaxy clusters that are gravitationally bound, and thus not subject to the same rate of recession due to cosmic expansion. The concept of the cosmic event horizon also forces us to grapple with the ultimate fate of the universe. In a universe dominated by dark energy, as ours appears to be, the expansion will continue to accelerate, leading to a scenario often referred to as the Big Rip, or, more likely, a heat death. In the latter, the universe expands indefinitely, thinning out into an increasingly cold, dark, and empty void. Stars burn out, black holes evaporate, and eventually even individual particles become so separated that no interactions can occur. The cosmic event horizon is an early symptom of this eventual cosmic desolation, a harbinger of a future where the grand cosmic drama we currently observe will have played itself out, leaving behind a silent, sterile expanse. This long-term perspective emphasizes the fleeting nature of our current cosmic abundance and the importance of scientific inquiry in documenting and understanding this era while it is still observable. Furthermore, the cosmic event horizon is distinct from a black hole's event horizon. While both represent boundaries beyond which information cannot escape, their origins and scales are vastly different. A black hole's event horizon is a localized phenomenon, a boundary in spacetime created by the immense gravity of a collapsed star or supermassive object. It is a point of no return for anything, including light that crosses it. The cosmic event horizon, on the other hand, is a global phenomenon, a boundary in the observable universe caused by the accelerating expansion of space itself. It doesn't represent a point of no return in the same sense as a black hole, but rather a limit to what we can ever hope to observe or interact with. Crossing a black hole's event horizon leads to certain doom. Crossing the cosmic event horizon is not something one can physically do, as it is a conceptual boundary defined by the limits of causality and light travel in an expanding universe. The existence of a cosmic event horizon also has profound implications for the search for extraterrestrial life and intelligence. If civilizations exist beyond our cosmic event horizon, we will never be able to detect them, and they will never be able to detect us. Their signals, even if broadcast at the speed of light, would be carried away by the expanding universe faster than they could ever reach us. This introduces a new layer of cosmic loneliness. We are not just limited by the vast distances between stars, but by the very structure of space-time that effectively isolates vast swathes of the universe from one another. This means that if we are to find other intelligent life, it must reside within our causally connected universe, within the realm from which light has had, and will continue to have, enough time to reach us. This significantly narrows the scope of our search, making the discovery of extraterrestrial intelligence an even more precious and improbable event. The interplay between the speed of light, the expansion of the universe, and the age of the universe is critical to understanding this boundary. The speed of light is our ultimate cosmic messenger, the fastest information can travel. However, over cosmic distances, the expansion of space itself can outpace even light. Imagine trying to run on a treadmill that is speeding up beneath your feet. If the treadmill speeds up faster than you can run, you will never reach the end, no matter how fast you're moving. Similarly, the light from distant galaxies travels towards us, but the space between us and those galaxies is expanding, effectively increasing the treadmill length. For objects beyond the cosmic event horizon, the rate of expansion between us and them is so high that the light they emit will never reach us regardless of how long it travels. This is a subtle but crucial distinction from simply being too far away. It's not just distance, it's the dynamic nature of space-time itself. This concept also challenges our intuitive understanding of now in the universe. When we look at distant galaxies, we're not seeing them as they are now, but as they were millions or even billions of years ago, when the light we are receiving began its journey. The cosmic event horizon pushes this even further, suggesting that there are parts of the universe whose now will never be accessible to us. Their present, their future, and even much of their past will remain forever hidden. This temporal disconnect adds another layer to the cosmic event horizon's significance. It's not just a spatial boundary, but a temporal one as well, dividing the universe into regions that are causally connected to us and those that are not. The cosmic event horizon therefore serves as a potent reminder of the limitations inherent in our existence within this particular universe. It is a boundary that no amount of technological prowess can overcome, a fundamental aspect of the cosmos that shapes our future exploration and understanding. It encourages us to cherish the observable universe we have, to delve into its mysteries with renewed vigour, knowing that this window of opportunity is not infinite. The galaxies we see today, the cosmic structures that inspire awe and wonder, are a temporary spectacle, a grand display that will eventually recede into the cosmic night. Our mission then is to witness, to understand, and to appreciate this fleeting grandeur before it becomes permanently inaccessible. This gives a sense of urgency to our exploration, a recognition that the universe we observe today is not the universe that will always be accessible. The profound beauty of this realization lies in its humbling power. It reminds us that despite our technological advancements and our boundless ambition, we are ultimately subject to the grand, overarching laws of the cosmos. The universe does not bend to our will, rather we must understand and adapt to its immutable principles. The cosmic event horizon is not a defeat, it is a definition, a clarification of the true scope of our potential journey. It tells us that while the universe is unimaginably vast, our ability to traverse it, even with the most advanced technology imaginable, is ultimately bounded by the very fabric of space-time itself. This boundary is not a limit to our curiosity or our imagination, but a limit to our physical reach, a cosmic truth that shapes our destiny among the stars. The very existence of this horizon compels us to consider the ethical implications of our cosmic journey. If our observable universe is finite and shrinking, what does that mean for the long-term survival of humanity? Should our efforts be focused on expanding our reach within this accessible domain, or should we prioritize the preservation and flourishing of life within the confines of our home planet and solar system? These are not easy questions, and the answers are far from clear. The cosmic event horizon also prompts us to contemplate the nature of reality itself. If vast portions of the universe are forever beyond our ability to observe, interact with, or even influence, do they truly exist in the same meaningful way as the parts that are accessible to us? This question touches upon deep philosophical debates about empiricism and the limits of human knowledge. While scientific consensus holds that the universe beyond our horizon is just as real as the part we can see, the practical implications for our understanding and interaction are undeniable. It creates a kind of cosmic partition, separating what is knowable and reachable from what is fundamentally unknowable and unreachable, at least through direct observation or physical travel. This distinction is crucial for setting realistic goals for interstellar exploration and for understanding the true scale of our cosmic neighborhood. Furthermore, the cosmic event horizon is not a fixed, static boundary. It is dynamic, evolving with the expansion of the universe. As dark energy continues to accelerate the expansion, the cosmic event horizon will continue to shrink, encompassing a smaller and smaller portion of the universe over time. This means that even galaxies that are currently within our observable universe could, in the distant future, recede beyond this boundary, becoming forever lost to future generations. This continuous shrinking adds another layer of urgency to our current astronomical endeavours. We are not just observing a static snapshot of the universe, we are witnessing a dynamic process of cosmic separation, a gradual fading of the distant lights. Every new telescope, every new observation, is therefore an attempt to capture as much information as possible from the accessible universe before it begins to disappear. The concept also has profound implications for the multiverse hypothesis. If our universe is just one of many, and if these other universes are beyond our cosmic event horizon, then they would be fundamentally undetectable and inaccessible to us. This doesn't necessarily disprove their existence, but it places them outside the realm of empirical science, at least for now. The cosmic event horizon, therefore, acts as a kind of ultimate barrier not just to physical travel, but also to our ability to verify certain cosmological theories that postulate realities beyond our immediate grasp. It emphasizes the importance of understanding the limits of our observational capabilities and distinguishing between what is scientifically verifiable and what remains in the realm of theoretical speculation. The cosmic event horizon also impacts our understanding of the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. The CMB represents the furthest back in time we can see, marking the point when the universe became transparent to light. However, even the CMB comes from a region that is now far beyond our current cosmic event horizon. The light we observe from the CMB today started its journey when the universe was very young and much smaller. Since then, the space from which that light originated has expanded dramatically, and that region is now receding from us at speeds far greater than light. So while we can observe the CMB, the source of that radiation is no longer within our causally connected universe in the present day. This illustrates the complex interplay between past observations and the current state of the expanding universe. In essence, the cosmic event horizon is a fundamental consequence of the universe's accelerating expansion, driven by dark energy. It defines the ultimate limit of what we can ever hope to reach, observe, or even influence. It is a boundary that forces us to confront our place in the grand cosmic tapestry, not as limitless explorers, but as temporary inhabitants of a vast, dynamic, and ultimately bounded cosmos. This understanding doesn't diminish the wonder of space exploration. Instead, it refines it, focusing our efforts on the accessible wonders and imparting a new sense of urgency to our cosmic quest. The stars we gaze upon, the galaxies we study, are not just distant lights. They are precious fragments of a universe that is slowly, inexorably, pulling itself apart, leaving us to contemplate the fading echoes of a grander, more connected past. Our lifetime, and indeed the lifetime of our civilization, is but a blink in this cosmic drama, and the cosmic event horizon ensures that we will only ever witness a fraction of the full play. This makes our current era of observation and potential exploration all the more significant, a fleeting opportunity to grasp the universe's true nature before much of it recedes into an eternal, unobservable night. Our understanding of what is truly accessible in the universe is intricately linked to the concept of the light cone, a fundamental construct in spacetime physics. Imagine a point in spacetime representing an event, perhaps a person standing on Earth at a specific moment. From this point, light can travel outwards in all directions, forming an expanding sphere. If we plot this on a spacetime diagram, with one axis representing time and the other three representing space, this expanding sphere of light forms a cone shape known as the future light cone. Everything within this future light cone is potentially causally connected to the initial event. That is, light or any other influence from that event could reach those points in space-time. Conversely, everything that could have possibly influenced that initial event lies within its past light cone, an inverted cone extending backwards in time. The boundaries of these light cones are defined by the speed of light, the universe's ultimate speed limit. Nothing can travel faster than light, meaning that any event outside an observer's past light cone could not have influenced them, and any event outside their future light cone cannot be influenced by them. This concept is not just a theoretical abstraction, it has profound practical implications for interstellar travel. When we consider travelling through space, we are not just traversing physical distances, we are navigating through space-time, and our journey is always confined within the boundaries of our light cone. For humans to travel through space, even at incredible speeds, they would always remain within their future light cone. The light cone essentially defines our sphere of influence and observation. Anything beyond our future light cone is, by definition, beyond our reach, not just physically, but causally. This means that if we launch a probe towards a distant star, the earliest that probe could arrive at that star, and the earliest any signal from it could return, is determined by the speed of light. Any journey, no matter how fast, must respect this fundamental speed limit. Now, let's connect this to the cosmic event horizon. While the light cone describes what is causally connected to a specific event or observer, the cosmic event horizon describes a global limit imposed by the accelerating expansion of the universe. The future light cone of an observer on Earth, if plotted over cosmic timescales, would eventually intersect with the cosmic event horizon. Beyond this intersection, points in space-time are receding from us at speeds greater than the speed of light due to cosmic expansion. This means that even if a signal were emitted from such a point, or if we were to try to travel to it, the expanding space would carry it away from us faster than the signal, or our spaceship could ever hope to cover the distance. So while our light cone defines what is theoretically reachable within the confines of special relativity, the cosmic event horizon defines what is practically reachable within the context of an expanding universe. The cosmic event horizon effectively shrinks our effective light cone over cosmic distances, cutting off portions of the universe that would otherwise be within our theoretical reach, based solely on the speed of light. This is a critical distinction, as it moves beyond the simple speed limit of light, and introduces the dynamic nature of space-time itself as a limiting factor. Consider a hypothetical scenario. If the universe were not expanding, or if its expansion were decelerating, our light cone would continue to expand indefinitely, eventually encompassing an ever larger portion of the universe. In such a universe, given enough time, we could theoretically reach any point, provided we could travel at or near the speed of light. However, in our universe, with its accelerating expansion, the cosmic event horizon acts as a kind of cosmic no-go area, a region that recedes from us faster than light can traverse. This means that even if we could travel at 99.999% the speed of light, there would still be vast swathes of the universe that would remain forever inaccessible to us, not because we're not fast enough, but because the space itself is expanding too quickly. This boundary is not a static wall, but a dynamic, ever-changing limit. As time progresses and the universe expands further, the cosmic event horizon effectively moves closer to us in terms of the number of galaxies it encompasses. Galaxies that are currently just within our observable universe, and thus within our light cone, will eventually cross the cosmic event horizon and recede beyond our ability to ever reach or even observe. This gradual disappearance of distant objects from our light cone is a sobering thought, highlighting the transient nature of our cosmic view. The light cone also helps us understand the concept of simultaneity in the universe. Because of the finite speed of light, there is no absolute now across vast cosmic distances. What is happening now on a distant exoplanet is only knowable to us after the light from that event has had time to travel across the intervening space. If that exoplanet is beyond our cosmic event horizon, then its now will never be accessible to us, its events forever unfolding in a causal bubble completely separate from our own. This reinforces the idea of cosmic isolation, where different regions of the universe are not just spatially separated, but also causally and temporally disconnected. For any human journey through space, the journey itself defines a new light cone for the traveller. As a spaceship accelerates and travels, its light cone shifts and expands, but it always remains bounded by the speed of light relative to its current frame of reference. However, the cosmic event horizon remains a global limit. No matter how fast the spaceship travels, it cannot escape the overall expansion of the universe. If it attempts to travel to a destination beyond the cosmic event horizon, that destination will simply recede faster than the ship can approach it. This distinction between the light cone and the cosmic event horizon is crucial for setting realistic expectations for interstellar travel. While the light cone tells us what is theoretically possible within the framework of special relativity, the cosmic event horizon tells us what is practically possible given the dynamics of our expanding universe. It means that even if we master near-light speed travel, our ultimate reach will still be constrained by the grand cosmological forces at play. Our efforts, therefore, must be focused on exploring the galaxies and cosmic structures that are gravitationally bound to our local group, or at least those that are not receding from us at an accelerating rate due to the expansion of space. The concept of the light cone also extends to the information we receive from the universe. Every photon, every neutrino, every gravitational wave that reaches us from a distant source is travelling along a path within its own light cone, eventually intersecting with our past light cone. The fact that we can observe the cosmic microwave background radiation is because the light from that early epoch is within our past light cone. However, as mentioned before, the source of that radiation is now far beyond our cosmic event horizon. This illustrates the dynamic nature of these cosmic boundaries and the complex relationship between past observations and present accessibility. Ultimately, the light cone and the cosmic event horizon combined paint a picture of a universe that is both vast and profoundly limited. While the universe contains billions of galaxies, only a fraction of them will ever be truly accessible to us, either through observation or physical travel. This limitation is not a flaw in our technology or our ambition, but a fundamental consequence of the laws of physics and the dynamics of the cosmos itself. It encourages us to appreciate the unique window of cosmic visibility we currently possess and to use it wisely, knowing that much of the universe's grandeur is, and will remain, forever veiled beyond these cosmic boundaries. Our journey through space, therefore, is not just a journey outwards, but a journey within the confines of our light cone, navigating the ever-present boundary of the cosmic event horizon. The human lifespan, in the grand scheme of cosmic time, is incredibly brief. Even with advancements in medicine potentially extending our lives, we're still talking about decades or perhaps a few centuries, a mere blink compared to the millions or billions of years involved in interstellar distances and cosmic phenomena. This fundamental limitation of our biological existence is a primary constraint on how far humans can realistically travel through space in one lifetime. Let's consider the fastest possible travel, near the speed of light. If we could achieve velocities approaching c, the speed of light, then the effects of relativistic time dilation would become significant. For an observer on a spaceship travelling at, say, 99% the speed of light, time would slow down considerably relative to an observer on Earth. This means that while only a few years might pass for the astronauts on board, decades or even centuries could pass on Earth. This effect, while fascinating, doesn't actually allow us to cheat the cosmic distance problem in the way many might imagine. Even with extreme time dilation, the journey still takes time from the perspective of the traveller. For example, a journey to the nearest star system, Alpha Centauri, which is about 437 light-years away. If you could travel at 99% the speed of light, it would take approximately 4.421 years of your subjective time for a one-way trip. A round trip would be about 8.82 years. This is certainly within a human lifetime, even a relatively short one. However, the catch is the immense energy required to accelerate a spacecraft, let alone a habitable one with humans on board, to such speeds. The energy requirements scale dramatically as you approach the speed of light, becoming effectively infinite as you get closer to c. Current and near-future propulsion technologies are nowhere near achieving such speeds. Chemical rockets, the workhorses of space travel, achieve speeds far less than 1% of the speed of light. Even advanced concepts like nuclear pulse propulsion or fusion rockets, while offering significant improvements, are still likely to be orders of magnitude slower than what's needed for relativistic travel. For instance, a nuclear pulse rocket might achieve speeds of around 5 to 10% of the speed of light. At 10% of the speed of light, a journey to Alpha Centauri would take about 43.7 years of subjective time. A round trip would be 87.4 years, pushing the limits of a single human lifetime, especially considering the time needed for acceleration and deceleration. This brings us to the core problem, the vastness of interstellar distances. Even at incredible speeds, the sheer scale of the galaxy means that most stars are simply too far away for a round trip within a single human lifetime, even with time dilation. If we consider destinations beyond Alpha Centauri, such as the Crab Nebula, which is about 6,500 light-years away, a journey at 10% the speed of light would take 65,000 years. Even at 99% the speed of light, it would still take over 6,500 subjective years for the travellers, an impossible duration for a single human life. Therefore, for practical interstellar travel within a single human lifetime, we are largely limited to our immediate cosmic neighbourhood. This includes our own solar system, and perhaps, with significant technological leaps, the very closest star systems. Even then, such journeys would be arduous, life-altering endeavours. A one-way trip to Alpha Centauri at 10% the speed of light would mean leaving Earth and arriving at a new star system as an elderly individual, having spent the majority of your life travelling in a confined space. Starting such a journey in your 20s would mean arriving in your late 60s or early 70s. This limitation has led to the exploration of alternative approaches to interstellar travel, such as generation ships. These are massive spacecraft designed to sustain multiple generations of humans over centuries or millennia, with the original crew dying en route and their descendants eventually arriving at the destination. While fascinating from a societal and engineering perspective, generation ships do not allow an individual to travel vast interstellar distances within their own lifetime. Instead, they represent a collective, multi-generational endeavour. Another concept is suspended animation or cryosleep. If humans could be safely put into a state of suspended animation for hundreds or thousands of years, and then reanimated without adverse effects, this would effectively extend a single, active lifetime. A person could go to sleep, travel for centuries, and wake up at their destination, having experienced only a brief period of subjective time. However, the technology for reliable long-term suspended animation for humans is purely theoretical at present, facing immense biological and technological hurdles. The challenges include preventing cellular decay, radiation damage over long periods, and the complex process of reanimation. The one-lifetime constraint is critical because it frames the nature of exploration. If exploration means an individual leaving and returning, or at least reaching a destination and having a meaningful experience there, then the distances we can cover are severely limited. If it means sending a probe or an automated system that collects data over millennia, that's a different proposition entirely. For human beings, the subjective experience of time and the biological imperative of a finite lifespan are paramount. Even within our solar system, journeys can be long and challenging. A trip to Mars can take 6 to 9 months one way. A round trip, including a stay on Mars, could easily span 2 to 3 years. Journeys to the outer solar system, to Jupiter or Saturn, would take several years one way. A mission to the Oort cloud, the furthest reaches of our solar system, could take decades. These are all within a human lifetime, but they are significant commitments of that lifetime. The limitations imposed by the finite human lifetime also influence the types of scientific missions we can undertake. Missions requiring long-duration human presence in deep space are constrained by radiation exposure, psychological effects of isolation, and the sheer logistical challenge of sustaining life for extended periods. While robotic probes can endure harsh environments and long travel times, humans require complex life support systems that add weight, complexity, and vulnerability to any long-duration mission. Therefore, when considering how far humans could travel through space in one lifetime, we must acknowledge the interplay of several factors: the speed of light as an ultimate limit, the immense energy requirements for relativistic travel, the vastness of interstellar distances, and the biological and psychological constraints of the human body. Without breakthroughs in propulsion that allow for sustained near-light speed travel with reasonable energy costs, or reliable long-term suspended animation, human interstellar travel within a single lifetime will remain largely confined to our immediate stellar neighbourhood. The dream of traversing vast cosmic distances in person, experiencing alien worlds firsthand, is tempered by the hard realities of physics and biology. Our current cosmic reach, in terms of direct human presence, is primarily limited to our solar system, with tantalizing but extremely challenging prospects for reaching the very closest stars within a single, dedicated human lifespan. The universe, in its immense scale, often leaves us feeling both awestruck and profoundly limited. Interplay of several factors: the speed of light as an ultimate limit, the immense energy requirements for relativistic travel, the vastness of interstellar distances, and the biological and psychological constraints of the human body. Without breakthroughs in propulsion that allow for sustained near-light speed travel with reasonable energy costs, or reliable long-term suspended animation, human interstellar travel within a single lifetime will remain largely confined to our immediate stellar neighbourhood. The dream of traversing vast cosmic distances in person, experiencing alien worlds firsthand, is tempered by the hard realities of physics and biology. Our current cosmic reach, in terms of direct human presence, is primarily limited to our solar system, with tantalizing but extremely challenging prospects for reaching the very closest stars within a single, dedicated human lifespan. The universe, in its immense scale, often leaves us feeling both awestruck and profoundly limited. The dream of interstellar travel, while often framed in terms of physics and engineering, ultimately collides with the undeniable reality of the human body and mind. Even if we overcome the monumental challenges of propulsion and energy, the biological and psychological toll of a journey lasting decades, or even centuries, presents an entirely different set of hurdles. Imagine a crew confined to a relatively small space, isolated from Earth, for the entirety of their adult lives. The challenges are profound, touching upon every aspect of human existence. Physiologically, the human body is exquisitely adapted to Earth's gravity and its protective atmosphere. Prolonged exposure to microgravity, for instance, leads to bone demineralization, muscle atrophy, and cardiovascular deconditioning. While countermeasures like exercise regimens and specialized diets exist, they are designed for missions lasting months, not decades. Over a human lifetime, these effects could become debilitating, potentially rendering a crew incapable of performing complex tasks upon arrival at their destination, let alone surviving the higher gravity of an alien world should one exist. Radiation exposure is another critical concern. Beyond the protective embrace of Earth's magnetosphere, astronauts are bombarded by galactic cosmic rays and solar particle events. These high-energy particles can damage DNA, increasing the risk of cancer, cataracts, and neurological disorders. A journey to even the nearest star would expose a crew to cumulative radiation doses far exceeding anything experienced on the International Space Station, necessitating advanced shielding technologies that add immense mass to any spacecraft, further complicating propulsion. Furthermore, the closed-loop life support systems required for such long voyages introduce their own set of biological complexities. Recycling air, water, and waste perfectly for decades without replenishment is an engineering marvel, but it also creates a fragile ecosystem. The slightest imbalance, the introduction of a novel pathogen, or the failure of a critical component could have catastrophic consequences for the crew. The psychological impact is perhaps even more daunting. Humans are social creatures, deeply connected to their environment and their communities. A small crew, confined in an artificial habitat, far from any familiar sights or sounds for generations, would face unprecedented levels of isolation and sensory deprivation. The psychological effects could manifest as chronic stress, depression, anxiety, and interpersonal conflict. Studies on long-duration confinement, even in Earth-based simulations, reveal the challenges of maintaining morale, cohesion, and mental well-being among small groups. The sheer existential weight of being irrevocably separated from Earth, knowing that return is impossible within their lifetime, could be crushing. To mitigate these psychological challenges, innovative approaches are being explored. Virtual reality environments could offer a semblance of natural landscapes and social interaction, providing mental escapes from the cramped confines of the ship. Carefully selected and extensively trained crews, with robust psychological profiles and strong interpersonal skills, would be essential. Moreover, the design of the spacecraft itself could play a crucial role. Incorporating aesthetically pleasing spaces, natural light cycles, and even small contained ecosystems with plants could help alleviate the feeling of being in a sterile, artificial environment. However, these are palliative measures, not cures, for the fundamental human need for connection and a sense of belonging to a larger world. The concept of generational ships, where multiple generations live and die aboard the vessel before reaching the destination, introduces an entirely new layer of sociological and ethical considerations. How do you maintain a stable society, a coherent culture, and a shared sense of purpose over centuries? The original mission objectives might become diluted or forgotten over time, replaced by internal conflicts or new priorities. The genetic diversity of such a small population would also be a concern, potentially leading to inbreeding and increased susceptibility to diseases. Establishing robust social structures, educational systems, and governance models that can endure for hundreds of years in isolation is a monumental challenge, perhaps even more complex than the engineering feats required for the journey itself. The very notion of what it means to be human, to have a connection to a home planet, would be redefined for those born and raised in the void. Beyond the immediate challenges of propulsion and human resilience, the vast emptiness of interstellar space itself harbours numerous dangers that must be accounted for in any long-duration mission. It is not a sterile vacuum, but a dynamic and often hostile environment, brimming with unseen threats that could cripple a spacecraft or endanger its crew. Micrometeoroids and space dust, though individually tiny, pose a significant cumulative risk over interstellar distances. Travelling at relativistic speeds, even a grain of sand can possess kinetic energy equivalent to a rifle bullet, capable of puncturing hulls, damaging sensitive equipment, or even causing catastrophic damage to critical systems. While advanced shielding, like Whipple shields, can offer some protection, they are designed for the relatively sparse environment of the solar system. Interstellar space, particularly around nebulae or star-forming regions, can be denser with such particles, demanding exceptionally robust and redundant shielding, which, again, adds immense mass and complexity to the spacecraft. Designing a ship to withstand decades of such bombardment without significant degradation or failure is a formidable engineering challenge. Radiation, as previously mentioned, is a constant and pervasive threat. Galactic cosmic rays, originating from supernovae and other high-energy astrophysical phenomena, are highly energetic particles that can penetrate even thick shielding, causing cellular damage and increasing cancer risk. Solar particle events, while less frequent in interstellar space than within a star system, still pose a danger if the spacecraft passes near active stellar flares. Predicting and mitigating these unpredictable bursts of radiation would require sophisticated detection systems and rapid response protocols, such as seeking shelter in heavily shielded sections of the ship. The long-term effects of chronic low-level radiation exposure on human physiology are still not fully understood, making it difficult to precisely quantify the acceptable limits for a multi-decade journey. The impact on electronics and computer systems is also a concern, as radiation can cause single-event upsets or even permanent damage to microprocessors, requiring radiation-hardened components and extensive error correction protocols. Furthermore, the magnetic fields and plasma environments encountered in interstellar space are not uniform. While generally weaker than within a stellar system, variations can still interact with the spacecraft's systems, potentially inducing currents or affecting navigational equipment. The heliosphere, the protective bubble created by our sun's solar wind, shields us from much of the interstellar medium. Once outside this bubble, a spacecraft would be directly exposed to the interstellar magnetic field and the low-density, high-energy plasma that permeates the galaxy. Understanding these interactions and designing systems that can operate reliably in such an environment is crucial. The sheer emptiness of space also presents a challenge in terms of communication and navigation. Light-speed delays mean that real-time communication with Earth becomes impossible over interstellar distances. Messages would take years, even decades, to reach their destination, making immediate intervention or assistance from Earth impossible. Crews would need to be entirely self-sufficient, capable of handling any emergency or system failure without external guidance. Navigation would rely on incredibly precise star mapping and inertial guidance systems, with no GPS equivalents to rely upon. The accumulation of even tiny errors over decades could lead to a significant deviation from the intended trajectory, resulting in a missed target or an extended journey. Finally, while the probability is exceedingly low, the possibility of encountering unforeseen astrophysical phenomena cannot be entirely discounted. Rogue planets, undetected black holes, or even highly energetic gamma-ray bursts, though rare, represent existential threats for which current technology offers little defense. While we can predict and avoid known hazards, the universe is vast and still holds many mysteries. Preparing for the truly unexpected, the black swan events of interstellar travel is a philosophical and engineering dilemma that highlights the inherent risks of venturing into the unknown. The journey through interstellar space is not merely a passage from point A to point B, but a sustained confrontation with the fundamental forces and unpredictable elements of the cosmos. The prospect of human interstellar travel, while a testament to our ambition and ingenuity, raises a complex web of ethical and societal questions that extend far beyond the technical challenges. These are not merely academic discussions. They are profound considerations that could shape the future of humanity itself. One of the most immediate ethical dilemmas revolves around resource allocation. The immense financial and material resources required to mount an interstellar mission would be astronomical, potentially diverting funds from pressing terrestrial issues such as poverty, climate change, and global health. Is it morally justifiable to invest trillions of dollars in a speculative venture to another star when so many problems remain unsolved on Earth? Proponents argue that the long-term benefits, the survival of humanity, the acquisition of new knowledge, and the inspiration it provides, outweigh the short-term costs. Opponents contend that such an undertaking would be an irresponsible squandering of resources, prioritizing a distant dream over immediate needs. The selection of the crew for such a mission also presents significant ethical challenges. Who decides who gets to go, and on what basis? Should it be based on scientific expertise, genetic fitness, psychological resilience, or a combination of factors? The chosen few would effectively become the progenitors of a new branch of humanity, carrying the genetic and cultural legacy of Earth into the cosmos. This raises concerns about eugenics, discrimination, and the potential for creating an elite group with extraordinary power and privilege. Furthermore, what about the rights of those who are left behind? Would the departure of an interstellar ark be seen as an abandonment or as a beacon of hope? For generational ships, the ethical landscape becomes even more intricate. The first generation would be making a decision that irrevocably binds their descendants to a life of confinement and purpose dictated by their ancestors. Do future generations have the right to refuse the mission or to alter its course? How do we ensure that the values and objectives of the founding generation remain relevant and meaningful over centuries, or that the crew maintains a sense of autonomy and self-determination. The potential for social stratification, power imbalances, and even tyranny within such a closed, isolated society is a genuine concern, demanding careful consideration of governance structures and mechanisms for dispute resolution. The implications for potential extraterrestrial life are also paramount. If we were to encounter alien civilizations or even microbial life, what would be our ethical obligations? Should we intervene, observe, or avoid contact entirely? The prime directive from science fiction, advocating non-interference, reflects a deep-seated concern about the potential harm our presence could inflict on less developed species. Even if we encounter no intelligent life, the act of colonizing an exoplanet could irreversibly alter its pristine environment, raising questions about planetary protection and our responsibility as cosmic stewards. The very act of sending a probe, let alone a crewed mission, could be seen as an act of cosmic contamination. Finally, the societal impact on Earth would be profound. The successful launch of an interstellar mission could inspire a new era of scientific discovery and technological innovation, fostering a sense of global unity and purpose. Alternatively, it could exacerbate existing inequalities, leading to resentment and division if only a select few benefit from the endeavour. The psychological impact of knowing that humanity has spread its seeds to another star, or conversely, the existential dread of realising we are truly alone, would reshape our understanding of our place in the universe. The ethical considerations of interstellar travel are not mere footnotes to the scientific enterprise. They are fundamental questions about our values, our responsibilities, and our vision for the future of humanity. While the immediate challenges of interstellar travel are rooted in the physics of propulsion and the biology of the human body, the very fabric of the cosmos itself, dominated by unseen forces, plays a subtle yet profound role in defining the ultimate limits of our cosmic reach. Dark matter and dark energy, the enigmatic components that constitute approximately 95% of the universe's mass-energy content, shape the large-scale structure and evolution of the cosmos, indirectly influencing our ability to traverse it. Dark matter, an invisible substance that interacts gravitationally but not electromagnetically, forms the scaffolding upon which galaxies and galaxy clusters are built. Its gravitational pull holds galaxies together, preventing them from flying apart. While we cannot directly detect dark matter, its presence is inferred from its gravitational effects on visible matter. For interstellar travellers, dark matter itself does not pose a direct threat in the sense of a physical obstacle. However, understanding its distribution is crucial for mapping the gravitational landscape of the galaxy. A spacecraft traversing interstellar space would be subtly influenced by the gravitational potentials created by dark matter halos, potentially affecting long-duration navigation and trajectory planning. While these effects are minuscule over short distances, over thousands of light-years and centuries of travel, even tiny gravitational perturbations could accumulate, necessitating extremely precise gravitational mapping and real-time adjustments. More significantly, dark matter's influence on galaxy formation dictates where stars and planetary systems are most likely to be found. Regions of higher dark matter density are where the visible matter congregates, forming the stellar nurseries we might one day hope to reach. Conversely, vast voids in the cosmic web, where dark matter is sparse, are largely empty of stars, presenting immense, featureless stretches of space that would be even more challenging to traverse, offering no convenient waypoints or potential destinations. Thus, the distribution of dark matter indirectly guides our search for habitable exoplanets, focusing our attention on the galactic plane and within specific stellar neighbourhoods. Dark energy, on the other hand, is an even more mysterious force, responsible for the accelerating expansion of the universe. Unlike dark matter, which pulls things together, dark energy pushes things apart. Its influence becomes dominant on the largest cosmic scales, affecting the separation of galaxies and galaxy clusters. For interstellar travel within our own galaxy, the effects of dark energy are negligible. The Milky Way is a gravitationally bound system, and its internal dynamics are not being pulled apart by dark energy. However, for hypothetical intergalactic travel, dark energy presents an insurmountable barrier. As the universe expands at an accelerating rate, galaxies beyond a certain distance are receding from us faster than the speed of light. Even if a spacecraft could travel at near light speed, it would never be able to catch up with these distant galaxies, which are being carried away by the expansion of space itself. This means that while interstellar travel within our galaxy might be theoretically possible, intergalactic travel to truly distant galaxies will eventually become physically impossible, even with arbitrarily advanced propulsion. The universe is effectively tearing itself apart on the grandest scales, isolating galaxy clusters from one another over cosmological timescales. This fundamental limit imposed by dark energy means that our ultimate cosmic neighborhood, in terms of reachable destinations, is finite and shrinking over billions of years. Our cosmic reach is ultimately bounded not just by the speed of light, but by the very expansion of space itself. Understanding dark matter and dark energy is not just an academic pursuit for cosmologists. It provides a deeper context for humanity's place in the universe and the ultimate limits of our mobility. While these unseen forces do not directly impede a starship's journey through a stellar system, their overarching influence on cosmic structure and expansion defines the playing field for all future interstellar endeavours, subtly dictating where we might go and where we will forever remain bound. The universe, in its vastness and its hidden components, continually reminds us of our profound limitations and the awe-inspiring scale of existence. One of the most mind-bending consequences of Einstein's theory of special relativity, and one that directly impacts the feasibility and experience of interstellar travel, is time dilation. This phenomenon describes how time can pass at different rates for observers in relative motion or in different gravitational fields. For a spacecraft travelling at a significant fraction of the speed of light, time dilation becomes a double-edged sword. It offers a path to reach distant stars within a human lifetime, but at the cost of an irreversible separation from Earth's timeline. Consider a starship accelerating to, say, 99.9% of the speed of light. For the crew aboard the ship, time would pass significantly slower than for observers remaining on Earth. A journey that might take decades or even centuries from an Earthbound perspective could, for the astronauts, be compressed into a few years or a few decades of their subjective experience. This relativistic effect is not science fiction. It is a proven consequence of the laws of physics. For example, subatomic particles travelling at near-light speeds in particle accelerators decay much slower than their stationary counterparts, precisely in accordance with time dilation predictions. This phenomenon opens up the possibility of reaching stars that are hundreds or even thousands of light-years away within a single human lifetime, as measured by the crew. For instance, a journey to a star 100 light-years distant, if travelled at 99.999999% the speed of light, could theoretically be completed in just over a year for the crew, while 100 years would have passed on Earth. This apparent paradox is resolved by understanding that there is no absolute now in the universe. Time is relative to the observer's frame of reference. However, the immense energy required to accelerate a massive spacecraft to such relativistic speeds is staggering, approaching the total energy output of stars. The closer one gets to the speed of light, the more the effective mass of the object increases, demanding exponentially greater energy inputs. This is where the practical limitations of time dilation become apparent. Even if we could achieve such speeds, the crew would return to an Earth that has aged significantly, potentially many centuries in their future. All their loved ones, their culture, and perhaps even the civilization they left behind would be long gone or fundamentally transformed. The concept of home would become a distant, almost mythical memory. This temporal displacement introduces profound psychological and sociological challenges. The returning astronauts would be temporal refugees, out of sync with their home planet. They would have experienced a few years, while their descendants have lived for centuries. What kind of reception would they receive? Would their knowledge and experiences still be relevant? Would they even be able to communicate effectively with a society that has evolved beyond recognition? The very notion of a lifetime becomes ambiguous in this context, as a lifetime for the traveller is vastly different from a lifetime for those left behind. Furthermore, the journey itself, even with time dilation, is not without its subjective challenges. While the overall travel time might be compressed, the experience of being confined in a spacecraft for years, even if those years are subjectively shorter than the Earthbound equivalent, still represents a significant portion of a human lifespan. The psychological and physiological effects of long-duration spaceflight, as discussed earlier, would still apply, albeit over a shorter subjective period. The journey might feel short for the crew, but the universe they return to would be irrevocably aged. Time dilation, therefore, offers a tantalizing theoretical solution to the vastness of interstellar distances, allowing humans to traverse cosmic gulfs within their perceived lifespan. Yet, it simultaneously imposes a profound and irreversible separation from their temporal origins. It is a cosmic Faustian bargain, the ability to explore the stars in person, but at the cost of losing everything and everyone you once knew. This inherent trade-off highlights the deep philosophical and personal sacrifices inherent in truly long-duration interstellar travel, even with the most advanced physics at our disposal. The ultimate goal of interstellar travel for many is the discovery and potential colonization of habitable exoplanets, worlds beyond our solar system capable of supporting life. Our current understanding of habitability is largely centered on the Goldilocks zone, the region around a star where temperatures allow for liquid water on a planet's surface. However, the search for life, and thus the potential destinations for human travelers, is rapidly expanding beyond this narrow definition, driven by new discoveries and evolving scientific understanding. Initially, the focus was on Earth-like planets orbiting Sun-like stars. These are planets roughly the size of Earth, with a similar atmospheric composition, orbiting in the Goldilocks zone of a G-type main sequence star. Such worlds would offer the most familiar environment for human colonization, requiring the least amount of terraforming or adaptation. Telescopes like Kepler and TEIS have indeed identified thousands of exoplanet candidates, a small fraction of which fall into this category. The nearest such potentially habitable exoplanet, Proxima Centauri b, orbiting our closest stellar neighbour, is a prime target for future missions. However, the definition of habitability is becoming increasingly nuanced. Scientists are now considering a broader range of stellar types and planetary environments. For example, red dwarf stars, which are far more numerous and longer-lived than Sun-like stars, are now considered potential hosts for habitable planets. While red dwarfs are prone to powerful flares, and their planets would be tidally locked, one side always facing the star, models suggest that thick atmospheres could redistribute heat, and the sheer abundance of these stars means a higher probability of finding suitable worlds. Proxima Centauri b, again, is an example of such a planet. Beyond the Goldilocks zone, the concept of ocean worlds, or ice giants, with subsurface oceans, like Europa or Enceladus in our own solar system, is gaining traction. These moons, far from their parent star's habitable zone, could harbour liquid water oceans heated by tidal forces from their gas giant planets, potentially providing environments for chemosynthetic life. While not directly habitable for humans in the traditional sense, they represent tantalising targets for robotic exploration and could conceivably support human outposts in the distant future, perhaps in subsurface habitats. The discovery of such worlds expands the potential targets for interstellar missions beyond just rocky planets with surface water. Furthermore, the concept of rogue planets, planets ejected from their stellar systems and wandering through interstellar space, is also being explored. While these worlds would lack a star for warmth, some theories suggest that they could retain a thick insulating atmosphere, or possess internal heat sources, potentially harbouring subsurface oceans. Such worlds, though challenging to detect and even more challenging to reach, represent another unexpected avenue for life and potential future human outposts, freed from the constraints of orbiting a star. The search for biosignatures, the chemical indicators of life, is also evolving. Beyond looking for oxygen and water vapour, scientists are exploring a wider range of atmospheric gases and spectral features that could indicate biological activity. This broader approach increases the likelihood of detecting life on planets that might not fit our traditional definition of Earth-like. The James Webb Space Telescope is already beginning to provide unprecedented insights into exoplanet atmospheres, paving the way for more definitive detections in the future. Ultimately, the availability of diverse and potentially habitable worlds significantly impacts the motivation and direction of interstellar travel. If our galaxy is teeming with Earth-like planets, the impetus to reach them will be immense. If life is rare, or confined to more exotic environments, our mission profiles and expectations will need to adapt. The ongoing discoveries in exoplanetology are constantly refining our understanding of where life might exist, and consequently, where humanity might one day venture, pushing the boundaries of what we consider a habitable destination, and expanding the potential reach of a human lifetime spent among the stars. The universe, it seems, is far more creative in its potential for life than we once imagined. While the current scientific consensus places severe limitations on interstellar travel within a single human lifetime, the realm of theoretical physics occasionally offers glimpses of concepts that, if ever realized, could fundamentally alter these constraints. Wormholes and warp drives, staples of science fiction, represent potential pathways to circumvent the vast distances of space and the immutable speed limit of light. Wormholes, also known as Einstein-Rosen bridges, are hypothetical shortcuts through spacetime. Imagine space as a two-dimensional sheet. The conventional way to get from one point to another is to traverse the sheet. A wormhole, however, would fold the sheet, creating a tunnel that connects two distant points, allowing for instantaneous or near-instantaneous travel between them. The concept arises from solutions to Einstein's equations of general relativity, which describe how mass and energy warp spacetime. While mathematically possible, the existence of traversable wormholes remains highly speculative. The primary challenge with wormholes is their stability and traversability. Theoretical models suggest that any naturally occurring wormholes would likely be incredibly tiny, unstable, and collapse almost immediately. To create and maintain a traversable wormhole, an exotic form of matter with negative energy density, often referred to as exotic matter, would be required. This matter would exert a repulsive gravitational force, preventing the wormhole from collapsing. While negative energy density is not forbidden by physics, its existence and stability in quantities large enough to create a macroscopic, traversable wormhole are unproven and highly debated. Even if such matter exists, the energy requirements for creating and stabilizing a wormhole would be astronomical, far beyond any conceivable human technology. Furthermore, the act of traversing a wormhole could introduce paradoxes related to causality, further complicating their theoretical feasibility. Warp drives, popularized by Star Trek, offer another theoretical means of faster-than-light travel without violating the cosmic speed limit locally. The concept, most notably the Alcubierre drive, proposes that a spacecraft could create a warp bubble around itself, contracting spacetime in front of it and expanding it behind it. The spacecraft itself would remain stationary within this bubble, not moving faster than light relative to its immediate surroundings. However, the bubble itself, and thus the spacetime it occupies, could move at superluminal speeds relative to distant observers. Similar to wormholes, the Alcubierre warp drive also requires exotic matter with negative energy density to create and sustain the warp bubble. The energy requirements are also immense, potentially equivalent to the mass energy of an entire planet. Furthermore, the theoretical models of warp drives present other significant challenges, such as the potential for extreme tidal forces at the edges of the bubble, which could tear apart anything entering or exiting it, and the Cherenkov radiation of exotic particles that could be emitted, potentially destroying anything in the path of the warp bubble. The physics of generating, controlling, and safely navigating such a warp bubble are currently far beyond our understanding and technological capabilities. It is crucial to emphasize that both wormholes and warp drives are currently theoretical constructs, existing largely in the realm of mathematical solutions to general relativity rather than established physics. There is no experimental evidence for their existence, nor any clear pathway to their creation with current or even foreseeable technology. They represent unforeseen technologies in the truest sense, requiring fundamental breakthroughs in our understanding of space-time and matter that could be centuries or even millennia away. However, the continued exploration of these concepts by theoretical physicists highlights the human desire to overcome the limitations of the universe. They serve as a reminder that our current understanding of physics, while powerful, may not be complete. Just as humanity once believed that heavier-than-air flight was impossible, future discoveries could unveil entirely new principles that revolutionize our ability to travel through space. For now, they remain the stuff of dreams, offering a tantalizing, albeit distant, hope for truly rapid interstellar travel within a single lifetime, bypassing the agonizingly slow pace dictated by conventional physics. Despite the formidable challenges, the drive for interstellar travel persists, fueled by a grand vision of humanity's long-term future. This isn't just about curiosity or scientific exploration, it's increasingly viewed by some as a strategic imperative for the survival and flourishing of our species. One of the most compelling arguments for interstellar expansion is planetary protection and species survival. Earth, while our cradle, is not immune to existential threats. Asteroid impacts, supervolcano eruptions, catastrophic climate change, or even self-inflicted wounds like nuclear war or uncontrolled artificial intelligence could render our home planet uninhabitable. By establishing self-sufficient colonies on other worlds, humanity could effectively diversify its portfolio, ensuring that the extinction of life on Earth does not equate to the extinction of the human race. Interstellar travel, in this context, becomes an insurance policy for humanity, a multi-generational project to safeguard our future. Beyond survival, there is the inherent human drive to explore and to expand. Throughout history, humanity has pushed the boundaries of its known world, driven by a thirst for knowledge, new resources, and new horizons. Space exploration, and ultimately interstellar travel, represents the ultimate frontier. It promises to answer fundamental questions about our place in the universe. Are we alone? What other forms of life exist? How do planetary systems evolve? The scientific returns from even a single interstellar mission could be transformative, revolutionizing our understanding of physics, biology, and cosmology. The pursuit of interstellar travel also serves as a powerful catalyst for technological innovation. The sheer scale of the challenges demands breakthroughs in propulsion, life support, materials science, artificial intelligence, and energy generation that could have profound benefits for life on Earth. Technologies developed for deep space missions, much like those from the Apollo program, often find unexpected applications in everyday life, improving health, communication, and resource management. The ambitious goal of reaching another star could inspire generations of scientists and engineers, fostering a culture of innovation and problem-solving that benefits all of humanity. Furthermore, the prospect of interstellar travel offers a profound psychological and philosophical boost to humanity. It reminds us of our potential, our collective ingenuity, and our capacity for grand endeavours. In an era often characterised by short-term thinking and terrestrial conflicts, a unifying long-term vision of humanity's expansion into the cosmos could inspire global cooperation and foster a sense of shared purpose. It elevates our perspective beyond the immediate confines of Earth, reminding us that we are part of something much larger. The vision also includes the possibility of encountering and interacting with extraterrestrial civilizations. While the probability of such an encounter on our first interstellar journey is low, the potential implications are immense. Such an event could fundamentally alter our understanding of life, intelligence, and the universe itself. Even if we never find intelligent life, the discovery of microbial life on another world would be a scientific revelation of unprecedented magnitude. However, realizing this grand vision requires a long-term commitment on a scale unprecedented in human history. It demands sustained investment, global cooperation, and a willingness to embrace risk and uncertainty. It will likely span multiple generations, meaning that those who initiate the journey may never see its completion, and those who complete it may never know their origins. This requires a profound shift in human perspective, moving beyond individual lifetimes to embrace a collective, multi-generational destiny. The dream of interstellar travel, while currently constrained by harsh realities, remains a powerful testament to the enduring human spirit of exploration and the imperative to secure a future among the stars. It is a vision that transcends individual lives, speaking to the deepest aspirations of our species. While the allure of interstellar travel is undeniable, the colossal societal and economic costs associated with such an endeavour represent a monumental hurdle, potentially dwarfing even the technical challenges. A deep space mission, especially one seeking to cross interstellar distances, would necessitate a global commitment of resources and effort on a scale that has no historical precedent. Consider the financial outlay. Developing and constructing a starship capable of sustained relativistic travel, with advanced life support, radiation shielding, propulsion systems, and sophisticated AI, would cost trillions of dollars. This figure would likely encompass not just the direct manufacturing expenses, but also decades of research and development, testing, and infrastructure construction. To put this into perspective, the entire global GDP for a single year is currently around $100 trillion. An interstellar project could easily consume a significant fraction of this over several decades, or even centuries of development. The question then becomes, who pays for it, and what are the opportunity costs? Such an immense financial commitment would inevitably mean diverting resources from other critical areas. Funding for healthcare, education, poverty alleviation, infrastructure development, and environmental protection could be significantly curtailed. This raises profound ethical questions about priorities. Is the long-term survival and expansion of humanity into space worth the potential suffering or neglect of current generations on Earth? The economic burden could exacerbate global inequalities, with wealthier nations or corporations potentially dominating the space endeavour, while less affluent regions struggle with basic needs. This could lead to social unrest and political instability, undermining the very global cooperation needed for such a massive undertaking. Beyond direct financial costs, there are the human resource costs. An interstellar project would require the dedication of millions of the brightest scientific, engineering, and logistical minds, potentially for generations. These are individuals who could otherwise be contributing to solving terrestrial problems. While the technological spin-offs could be beneficial, the immediate impact would be a massive brain drain from other sectors of society. Training, educating, and supporting these individuals and their families would represent another significant societal investment. The long-term commitment required also presents a unique challenge in a world often driven by short-term political cycles and economic fluctuations. Maintaining consistent funding and public support for a project that might not yield tangible results for centuries would be incredibly difficult. Political leaders come and go, economic priorities shift, and public enthusiasm can wane. Sustaining a multi-generational project demands an unprecedented level of foresight, stability, and collective will from global society. Furthermore, the societal impact of the mission itself, once launched, could be profound. A generational ship carrying a significant portion of humanity's genetic and cultural heritage would represent a profound change in how we view ourselves. The act of sending such a ship might be seen as an admission of Earth's ultimate unsustainability, leading to existential anxieties. Conversely, it could inspire hope, but the cost to those left behind, both tangible and intangible, would be immense. The potential for social division between spacefaring and earthbound factions could also arise, creating new forms of inequality and identity. Finally, there are the unforeseen costs. What if the mission fails catastrophically? What if the destination world is unsuitable or already inhabited by hostile life? The loss of lives, resources, and decades of effort would be a devastating blow, not just financially but psychologically and socially. The return on investment for such a high-risk, high-reward endeavour is far from guaranteed, making the decision to undertake it a profound gamble with humanity's collective future. The societal and economic burden of interstellar travel is not merely a logistical challenge, it is a fundamental test of our values, our priorities, and our capacity for long-term, collective sacrifice.